Something about our universe doesn't add up. Scientists have spent decades mapping the cosmos, calculating the mass of galaxies, and trying to understand what holds them together. But there's a problem, one so massive that it rewrites the very fabric of how we think the universe works. It's the mystery of dark matter, the invisible substance that supposedly makes up most of the mass in the universe. Except, what if some galaxies don't have it at all? That's right. Astronomers have discovered entire galaxies that seem to be missing dark matter completely. And that shouldn't be possible. If dark matter is the glue that holds galaxies together, then how are these galaxies even existing? Are our theories about dark matter completely wrong? Could we be missing something even bigger? This is one of the most mind-bending mysteries of space, and the deeper we go, the stranger it gets. To understand why this is so bizarre, let's back up a little. For years, scientists have believed that dark matter is the backbone of the universe. It doesn't emit light, it doesn't interact with normal matter in the way we expect, and yet, it seems to make up about 85% of the total mass in the cosmos. We can't see it, but we can see what it does. Galaxies spin faster than they should, based on the visible matter alone. If dark matter wasn't there, galaxies would tear themselves apart. That's why this discovery is so shocking. These dark matter-free galaxies don't seem to follow the same rules. And if we can't explain them, it might mean that everything we thought we knew about the universe is incomplete. The first big shock came in 2018, when astronomers using the Dragonfly Telephoto Array telescope spotted a galaxy called NGC 1052 DF2, or just DF2 for short. It's a faint, ghostly galaxy floating 65 million light-years away in the constellation Cetus. At first glance, it looked like a typical ultra-diffuse galaxy, a type of galaxy that's faint and spread out, almost like a cosmic mist. But when scientists measured how fast the stars inside DF2 were moving, they noticed something that made no sense. The stars were moving way too slowly. Why does that matter? Because the speed of stars in a galaxy tells us how much mass is holding them together. The faster they move, the more mass there has to be. In a normal galaxy, dark matter makes up most of that mass, keeping everything from flying apart. But DF2's stars were moving so slowly that the galaxy barely seemed to have any dark matter at all. It was as if it was made only of the visible stars and gas, nothing more. That was the first red flag. Scientists checked and rechecked their data, trying to explain what they were seeing. Maybe the measurements were wrong. Maybe the telescope was giving false readings. But every test confirmed the same thing. DF2 had almost no dark matter. And it wasn't alone. Just a year later, astronomers found another galaxy, DF4, which also seemed to lack dark matter. That's when things got even weirder. If there were two galaxies without dark matter, there could be more. And that raised a terrifying question. Are we completely wrong about how galaxies form? Up until this point, everything we thought we knew about galaxy formation relied on dark matter playing a key role. Without it, the universe doesn't make sense. So how did these galaxies form? Did something strip them of their dark matter, or were they born this way? If so, what does that mean for the rest of the universe? One theory suggests that these galaxies lost their dark matter due to interactions with larger galaxies. If a massive galaxy passed nearby, its gravitational pull could have stripped away dark matter from DF2 and DF4, leaving them as husks of normal matter floating in space. But that explanation has problems. First, dark matter doesn't interact with normal matter in the way we expect. If these galaxies lost dark matter, why didn't they lose stars too? And why are they still so stable? Another possibility is that they never had dark matter to begin with. But that's even harder to explain. If dark matter is necessary for galaxies to form, how did these galaxies exist at all? Did they somehow form in a completely different way, defying everything we know? If so, that could mean dark matter isn't as essential as we thought, or worse, that we don't understand it at all. Some scientists have even suggested that these galaxies might be evidence that dark matter doesn't exist in the way we think. Maybe gravity itself behaves differently on cosmic scales, and what we call dark matter is actually just a misunderstanding of how gravity works in deep space. This idea, known as modified Newtonian dynamics, or MOND, proposes that the laws of physics change at large distances, which could explain the strange behavior of galaxies without requiring dark matter at all. But there's a big problem with that idea. If dark matter isn't real, then how do we explain the galaxies that do follow the rules? We see dark matter's effects everywhere, in the rotation of galaxies, in the cosmic web that connects clusters of galaxies, and even in the way light bends around invisible mass. If dark matter-free galaxies exist, but most galaxies need dark matter to stay together, then something isn't adding up. The mystery gets even deeper when you consider how rare these galaxies are. If dark matter-free galaxies exist, why aren't there more of them? Why do we only see a handful, while most galaxies follow the expected patterns? If dark matter is truly everywhere, how did these few galaxies escape it? Some astronomers think these galaxies could be cosmic outliers, formed under unique conditions that made them different from the rest. But others believe they could be a sign of something much bigger, a flaw in our understanding of the universe itself. And then there's the ultimate question: if some galaxies can exist without dark matter, could we? The Milky Way is held together by dark matter, or at least, that's what we assume. But if galaxies like DF2 and DF4 exist, is it possible that our own galaxy is different from what we think? Could our measurements of dark matter be wrong? Or worse, could dark matter be something entirely different from what we've imagined? The more we look, the more questions we find. New telescopes, like the James Webb Space Telescope, are searching deeper into the cosmos, trying to uncover more about these strange galaxies. But every answer leads to more mysteries. Are there entire regions of space where dark matter doesn't exist? Could there be new laws of physics waiting to be discovered? Or are we standing at the edge of an even bigger cosmic truth, one that could rewrite the history of the universe itself? The more we explore dark matter-free galaxies, the stranger the mystery becomes. If these galaxies exist, then they must have formed in a completely different way than what we thought was possible. But how? To understand just how bizarre this is, let's break down what we know about galaxy formation and why dark matter is supposed to be essential. In the early universe, shortly after the Big Bang, everything was hot, chaotic, and expanding. The first structures in the universe formed from tiny fluctuations in density. Some regions had slightly more mass than others, and over time, gravity pulled matter together into clumps. These clumps eventually grew into galaxies. But here's the catch: ordinary matter alone wasn't enough to make this happen. The universe was expanding so fast that if galaxies had to form just from normal matter, there wouldn't have been enough gravity to pull everything together. Instead, scientists believe that dark matter, an invisible, massive substance, was the real force shaping galaxies. It provided the extra gravitational pull needed to bring gas and stars together, creating stable galaxies. Without dark matter, the process wouldn't work. And yet, DF2 and DF4 exist. That means either they formed in some unknown way, or our entire understanding of galaxy formation is wrong. Some astronomers have proposed an explanation. These galaxies could have formed in environments where dark matter was somehow left behind. One idea is that they were once part of larger galaxies, but something stripped them of their dark matter. If a massive galaxy passed by, its gravitational pull could have stolen the dark matter from DF2 and DF4, leaving them with only their visible stars and gas. But that explanation raises new questions. If dark matter is supposed to be nearly impossible to interact with, if it doesn't collide, clump, or break apart like normal matter, then how could it be stripped away so easily? If it was removed, why didn't the stars get ripped away too? And why do DF2 and DF4 still appear stable, instead of flying apart like we'd expect? Another possibility is that these galaxies never had dark matter in the first place. Maybe they formed in regions of the universe where dark matter wasn't present. But that idea is even harder to explain. The standard model of cosmology says that dark matter is everywhere, shaping the formation of all galaxies. If DF2 and DF4 formed without it, that would mean our models are missing something huge. There's also the possibility that these galaxies are illusions. Maybe they aren't actually missing dark matter, but instead, something about them is fooling our instruments. For example, What if DF2 and DF4 aren't actually where we think they are? If we've miscalculated their distance, their mass estimates could be wrong, making it seem like they lack dark matter when they actually don't. But so far, multiple measurements confirm that these galaxies are real, and their lack of dark matter isn't just a mistake. That leaves us with a more radical possibility. Maybe dark matter itself isn't real in the way we think. What if the laws of gravity work differently in space than they do on Earth? This idea, called modified Newtonian dynamics, MOND, suggests that instead of dark matter being a hidden substance, gravity itself behaves differently on cosmic scales. If true, it would mean that we don't need dark matter to explain galaxies. We just need to change our understanding of gravity. But there's a massive problem with that. If MOND were correct, we'd expect all galaxies to follow its predictions. Instead, most galaxies behave exactly as if they contain dark matter. We see the effects of dark matter everywhere, in galaxy clusters, in the bending of light due to gravitational lensing, and even in the cosmic microwave background, the afterglow of the Big Bang. So if dark matter doesn't exist, we still need an explanation for all of these other phenomena. Meanwhile, astronomers keep finding more potential dark matter-free galaxies. If there were only one or two, we could dismiss them as weird cosmic accidents. But if there are more, then something much bigger is going on. What if entire regions of the universe contain galaxies without dark matter? What if dark matter isn't as uniform as we assumed? What if the very nature of the universe is more complex than we ever imagined? The James Webb Space Telescope and other advanced observatories are now hunting for more dark matter-free galaxies. If they find more, it could force scientists to rethink everything from the Big Bang to the fate of the universe. But even if they don't, the fact that even one galaxy without dark matter exists is already enough to shake the foundations of modern physics. So what does this mean for the future of astronomy? Are we on the verge of discovering a new force of nature? Are dark matter-free galaxies the key to unlocking a deeper truth about the cosmos? Or are we just seeing the tip of an even greater mystery, one that will take decades, or even centuries, to fully understand? The deeper we look into space, the more mysteries we find. And with every answer, the universe only seems to become more mysterious. If these dark matter-free galaxies are real and more of them exist, then our entire understanding of cosmology could be at stake. For decades, dark matter has been the invisible force shaping the universe, holding galaxies together, and influencing the motion of stars. But if some galaxies can form and exist without it, then dark matter might not be as essential as we thought. That raises an unsettling question. Have we been wrong about the fundamental structure of the universe all along? One of the biggest problems with dark matter-free galaxies is that they defy the predictions of our best cosmological models. The lambda cold dark matter model, which has been the foundation of modern cosmology, depends on dark matter making up about 85% of the universe's mass. This model successfully explains the large-scale structure of the universe, the rotation of galaxies, and the cosmic microwave background radiation. But if galaxies like DF2 and DF4 don't have dark matter, then our models might be missing something crucial. Some scientists believe that dark matter might not be as uniformly distributed as we assumed. Traditionally, dark matter is thought to form massive halos around galaxies, influencing how they move and evolve. But what if, in rare cases, these halos don't form? What if dark matter can be separated from ordinary matter under certain conditions? This idea challenges the notion that dark matter is always present wherever galaxies form. To explore this possibility, astronomers are searching for more dark matter-free galaxies. If only a few exist, they might be anomalies, strange cosmic accidents. But if many more are discovered, then something deeper is happening. Could there be entire clusters of galaxies without dark matter? Could there be entire regions of the universe where dark matter behaves differently than we expect? One leading theory is that these galaxies might have been stripped of their dark matter through extreme interactions with other galaxies. In the chaotic environment of galaxy clusters, smaller galaxies can be torn apart by the gravitational forces of their larger neighbors. If DF2 and DF4 were once part of a larger system, their dark matter could have been pulled away, leaving only the visible stars behind. But there's a major issue with this explanation. If their dark matter was removed, then their stars should have been disrupted too. Without dark matter holding them together, DF2 and DF4 should have been torn apart by tidal forces. Instead, they appear to be stable and intact, behaving like normal galaxies, just without the dark matter. This suggests that whatever process removed the dark matter was selective, affecting only the invisible mass while leaving the stars untouched. Another possibility is that these galaxies never had dark matter in the first place. But this raises another paradox. How could a galaxy form without dark matter? If dark matter is responsible for pulling gas and dust together to form galaxies, then DF2 and DF4 shouldn't exist at all. One radical idea suggests that dark matter might not be necessary for galaxy formation in certain conditions. Perhaps under specific circumstances, galaxies can form purely through the gravitational influence of ordinary matter. If true, this would mean that our understanding of galaxy formation needs to be revised. Some astronomers are considering alternative explanations that don't involve dark matter at all. One possibility is that the way we measure these galaxies is flawed. If DF2 and DF4 are closer or farther than we think, then our mass estimates could be wrong, making it seem like they lack dark matter when in reality they don't. However, multiple independent measurements confirm that these galaxies are at the expected distances, reinforcing the idea that they truly lack dark matter. This leads us to another, even more controversial possibility. Maybe dark matter itself isn't real. For decades, the idea of dark matter has been supported by indirect evidence. We can't see it, but we see its gravitational effects on galaxies. It explains why galaxies rotate the way they do, why galaxy clusters behave the way they do, and why the cosmic web of the universe looks the way it does. But if dark matter-free galaxies exist, then maybe we've been misunderstanding gravity all along. This idea is at the core of MOND, modified Newtonian dynamics, a theory that suggests that gravity behaves differently on cosmic scales. According to MOND, instead of dark matter being an unseen substance, the force of gravity itself changes in ways we don't fully understand. If MOND were true, then galaxies wouldn't need dark matter to explain their motion. Instead, their stars would follow different gravitational rules at extremely low accelerations. But MOND has problems. While it can explain certain anomalies in galaxy rotation, it fails to account for other cosmic observations, like the large-scale structure of the universe and gravitational lensing. In contrast, dark matter explains these phenomena remarkably well. If dark matter-free galaxies are real, they could provide the ultimate test for MOND. If these galaxies truly lack dark matter and still obey the expected gravitational laws, then MOND might gain support. But if these galaxies behave inconsistently with MOND's predictions, then dark matter remains the best explanation. Meanwhile, astronomers are using advanced telescopes to study DF2, DF4, and other potential dark matter-free galaxies in greater detail. The James Webb Space Telescope, with its powerful infrared vision, is providing new insights into these galaxies. If it confirms that they lack dark matter, then the mystery deepens. Could there be a hidden force at play that we don't yet understand? Could dark matter exist in multiple states, some of which are undetectable? Or could these galaxies be the first signs that we need a completely new theory of the universe? Whatever the answer, dark matter-free galaxies represent one of the greatest puzzles in modern astrophysics. They challenge the very foundation of our understanding of the cosmos. And as astronomers continue to probe deeper into the universe, we may be on the brink of a scientific revolution, one that forces us to rewrite everything we thought we knew about the nature of reality itself. The mystery of dark matter-free galaxies isn't just about a few strange objects in space. It's about whether our entire framework for understanding the universe is correct. If dark matter is essential for galaxy formation, then these galaxies shouldn't exist. And yet they do. That means we're either missing a major piece of physics, or our theories need a complete overhaul. Let's step back for a moment and consider the significance of this. Imagine if we discovered a planet that didn't obey gravity. If everything else in the universe followed the laws of physics as we know them, but this one planet floated freely, seemingly unaffected by any gravitational force, it would force us to rethink how gravity works. That's what dark matter-free galaxies are doing to cosmology. For decades, dark matter has been the invisible glue that holds galaxies together. It explains why galaxies don't fly apart as they spin, why galaxy clusters stay bound, and why the large-scale structure of the universe looks the way it does. If dark matter isn't real, or if it's behaving differently than we thought, then we have to reconsider everything from the Big Bang to the expansion of the universe. Astronomers are now searching for more dark matter-free galaxies to see if DF2 and DF4 are anomalies or part of a larger pattern. If more galaxies like them exist, then we need to explain why. Could there be entire clusters of galaxies without dark matter? Could dark matter behave differently in certain parts of the universe? One theory suggests that these galaxies might have formed in an environment where dark matter was naturally absent. If dark matter is usually present in massive halos around galaxies, then how could a galaxy form without it? Some researchers believe that under extreme conditions, it might be possible for galaxies to form purely through the gravitational interactions of ordinary matter. This would require a completely new understanding of galaxy formation, one that doesn't rely on dark matter at all. Another idea is that dark matter in these galaxies was somehow stripped away. In dense galaxy clusters, interactions between galaxies can be violent. A smaller galaxy passing through a massive one could have its dark matter halo pulled away by gravitational forces, leaving only the visible stars behind. But there's a problem. If dark matter was removed, the stars should have been affected too. Yet DF2 and DF4 appear stable, suggesting that whatever process removed their dark matter was highly selective. This raises another possibility. What if dark matter exists in multiple forms? We think of dark matter as a single, invisible substance, but what if there are different types of dark matter, some of which are more easily stripped away than others? If dark matter can exist in different states, it could explain why some galaxies appear to lack it. The discovery of these galaxies also brings us back to one of the biggest debates in physics: whether dark matter is a real substance, or just a misunderstanding of gravity. If dark matter-free galaxies exist, then modified Newtonian dynamics, MOND, might provide an alternative explanation. MOND suggests that gravity behaves differently at low accelerations, meaning that we don't need dark matter to explain the motion of galaxies. But MOND has struggled to explain many aspects of cosmology, especially the way galaxies cluster together, and how light bends around massive objects due to gravitational lensing. If MOND were correct, we'd expect all galaxies to behave in a way that aligns with its predictions. Instead, most galaxies behave exactly as if they contain dark matter, making MOND less likely. However, if we find more dark matter-free galaxies and they follow MOND's predictions, then the theory might gain new credibility. This would be one of the biggest paradigm shifts in physics, comparable to Einstein's discovery of relativity. Meanwhile, the James Webb Space Telescope and other observatories are continuing the hunt for more of these strange galaxies. If they confirm that dark matter-free galaxies exist in significant numbers, we'll need to rethink everything we know about how galaxies form and evolve. Could these galaxies be telling us that dark matter isn't real? Could they be revealing an unknown force in the universe? Or are they simply rare cosmic accidents that challenge our current models? One thing is certain: the deeper we look into space, the more mysteries we find. And every time we think we understand the universe, it surprises us with something we never expected. If DF2 and DF4 are not anomalies but part of a broader cosmic phenomenon, then the implications for physics are staggering. For decades, our entire model of the universe has depended on the idea that dark matter exists and is responsible for the formation and stability of galaxies. The standard model of cosmology, known as lambda cold dark matter, relies on the assumption that dark matter makes up the majority of the universe's mass. If even a small fraction of galaxies can exist without it, then lambda cold dark matter may need to be revised, or even replaced. But let's break this down even further. If dark matter is real, then there must be a reason why DF2 and DF4 don't have any. Did they form in a way that prevented dark matter from accumulating? Were they stripped of their dark matter by an unknown force? Or, even more bizarrely, Could dark matter exist in multiple states, some of which are undetectable by our current instruments? One possible explanation is that DF2 and DF4 underwent a violent event in their past. Galaxies don't exist in isolation, they interact, merge, and collide with one another. Some researchers believe that these galaxies might have experienced a gravitational encounter so extreme that their dark matter was stripped away, leaving only the stars behind. This process, known as tidal stripping, is thought to occur in dense galaxy clusters where gravitational forces are incredibly strong. However, this theory has a problem. If dark matter was pulled away by gravitational interactions, then the visible stars should have been affected as well. Yet DF2 and DF4 appear to be stable, with no evidence that they were disrupted. If dark matter was removed, why did the stars remain undisturbed? This suggests that whatever process removed the dark matter must have been highly selective, affecting only the invisible mass while leaving the luminous matter intact. Another hypothesis is that these galaxies never had dark matter to begin with. This is an even more radical idea because it challenges our understanding of how galaxies form. According to our current models, dark matter is essential in the early universe because it provides the gravitational pull needed to gather gas and dust into galaxies. If DF2 and DF4 formed without dark matter, then we need an entirely new theory of galaxy formation. Some researchers suggest that these galaxies might have formed in an environment where dark matter was naturally absent. Perhaps under specific conditions, such as in regions with extremely low-density dark matter, galaxies can form purely from ordinary matter. But if that's the case, then why don't we see more galaxies like DF2 and DF4? Why are they so rare? This leads us to another possibility. What if dark matter itself isn't a single, uniform substance? We tend to think of dark matter as one mysterious, invisible entity, but what if it comes in different forms? If dark matter can exist in multiple states, then perhaps DF2 and DF4 contain a type of dark matter that doesn't interact with normal matter in the way we expect. This could explain why our instruments fail to detect it. Alternatively, what if dark matter is not a physical substance at all, but instead a fundamental property of space itself? Some scientists have proposed that dark matter might be an emergent effect of gravity, something that only appears to exist when we observe galaxies at large scales. This idea ties into modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at extremely low accelerations. If MOND is correct, then we don't need dark matter to explain the motion of galaxies. Instead, the laws of gravity themselves would need to be rewritten. But MOND has struggled to explain several key observations, such as the cosmic microwave background and gravitational lensing. If dark matter-free galaxies exist, they could provide a crucial test for MOND. If these galaxies behave exactly as MOND predicts, then the theory might gain new support. Meanwhile, astronomers are using the most advanced telescopes available to study these galaxies in greater detail. The Hubble Space Telescope provided the first clues, but now the James Webb Space Telescope is taking an even closer look. With its infrared capabilities, JWST can peer deeper into these galaxies to analyze their structure, their star populations, and their dynamics. If JWST confirms that DF2 and DF4 truly lack dark matter, then the mystery deepens even further. Could these galaxies be revealing a hidden aspect of the universe that we've never considered? Could they be pointing us toward a new force of nature, something beyond the four fundamental forces we currently recognize? Or are they simply cosmic outliers, rare exceptions to the general rule? The truth is, we don't know yet. But what we do know is that every time we think we have the universe figured out, it throws something unexpected at us. The existence of dark matter-free galaxies is one of the most puzzling discoveries in modern astrophysics. And as we continue to study them, we might be on the verge of uncovering a new, fundamental truth about the cosmos, one that could change our understanding of the universe forever. The very existence of dark matter-free galaxies threatens to upend our most fundamental understanding of how the universe works. Everything we think we know about galaxy formation, the structure of the cosmos, and even gravity itself has been built on the assumption that dark matter is an essential ingredient in the universe. Yet, here we are, staring at galaxies like DF2 and DF4, which appear to have formed and evolved without it. If these galaxies are not anomalies but instead represent a new category of cosmic structures, then every model we have relied upon for nearly a century could be flawed, or, at the very least, incomplete. This realization is both thrilling and terrifying because it means we might be missing a crucial piece of the cosmic puzzle, a piece that could rewrite the laws of physics as we know them. But before we throw out everything we know about dark matter, we have to ask, could we simply be misunderstanding what we are seeing? After all, science has a long history of interpreting strange observations incorrectly before finally arriving at the right explanation. The first possibility we must consider is that DF2 and DF4 are not truly devoid of dark matter, but rather that our methods for detecting it are flawed in some way. Dark matter is, by definition, invisible. It does not emit, absorb, or reflect light. Instead, its presence is inferred through gravitational effects, particularly by analyzing the rotation curves of galaxies. Typically, astronomers observe that the outer regions of galaxies rotate faster than they should based on visible matter alone, implying the presence of an unseen mass, dark matter. However, when this same method was applied to DF2 and DF4, the expected gravitational influence was missing. The stars moved at speeds that aligned perfectly with the visible matter present, suggesting that there was no additional hidden mass. So, if our measurements are correct, and these galaxies really are lacking dark matter, the next question is, how did they form? According to the standard model of cosmology, galaxies emerge within massive halos of dark matter. In the early universe, dark matter's gravitational pull helped gather gas and dust, leading to the formation of stars and, eventually, galaxies. If dark matter is truly a necessary ingredient in galaxy formation, then DF2 and DF4 should not exist. Yet they do, which means either our understanding of galaxy formation is incomplete, or an alternative mechanism allowed these galaxies to come into existence without dark matter. One potential explanation is that these galaxies were formed through a process unlike anything we have previously considered. Perhaps, under very specific conditions, it is possible for galaxies to form without relying on dark matter at all. Some researchers have proposed that DF2 and DF4 might have originated in environments where the normal balance of matter and dark matter was disrupted. For example, if a galaxy were to form in a region of space where dark matter was unusually sparse or distributed unevenly, it might end up lacking the invisible mass that other galaxies rely on. This would imply that dark matter is not as universally distributed as we thought, and that certain areas of the universe might be naturally deficient in it. Another possibility is that DF2 and DF4 did originally contain dark matter but lost it through some unknown mechanism. One theory suggests that these galaxies may have experienced a violent interaction with a much larger galaxy, which could have stripped them of their dark matter halo. This process, known as tidal stripping, occurs when a smaller galaxy passes too close to a massive neighbor, and the gravitational forces pull away its dark matter. However, this explanation presents a major problem. If dark matter was stripped away, then the stars and gas within the galaxy should have been affected as well. The lack of any significant disturbance in the visible matter suggests that whatever removed the dark matter did so in a highly selective manner, something we do not yet understand. This raises an even stranger possibility. What if dark matter itself is not a single, uniform substance but instead exists in multiple forms? If dark matter is not just one thing but instead comes in different states, some of which can be more easily stripped away than others, this could explain why DF2 and DF4 appear to lack it. Some physicists have speculated that dark matter might include both cold and warm varieties, each behaving differently under different conditions. If DF2 and DF4 somehow lost only one type of dark matter while retaining another that is currently undetectable, it would mean that our current models of dark matter are far too simplistic. But the mystery does not stop there. If dark matter is not responsible for holding these galaxies together, then what is? In most galaxies, dark matter provides the extra gravitational pull needed to prevent stars from flying apart. Without it, we would expect galaxies like DF2 and DF4 to be unstable, yet they appear to be holding together just fine. This suggests that either an entirely different force is at play, or the fundamental laws of gravity do not work the way we think they do. This brings us to one of the most controversial ideas in modern physics: the possibility that dark matter does not exist at all and that what we perceive as dark matter is actually a misunderstanding of gravity itself. This idea is known as modified Newtonian dynamics, or MOND. According to MOND, gravity behaves differently at extremely low accelerations, meaning that the need for dark matter disappears entirely. Instead, the strange behavior we see in galaxies is simply the result of gravity working in a way we have not yet fully understood. If MOND is correct, then DF2 and DF4 could be providing the missing piece of evidence needed to support it. But there is a catch. MOND has struggled to explain many other cosmic observations, particularly the large-scale structure of the universe and gravitational lensing, which is the bending of light around massive objects. If MOND were the correct explanation, then we would expect all galaxies to behave in a way that aligns with its predictions, yet most galaxies seem to fit the dark matter model much better. This means that while DF2 and DF4 might be interesting anomalies, they alone are not enough to overturn decades of evidence in favor of dark matter. As astronomers continue to study these galaxies, they are also searching for more examples. If DF2 and DF4 are the only dark matter-free galaxies, then they might simply be rare cosmic accidents. But if more galaxies like them are found, it would mean that this is not a coincidence but a fundamental aspect of the universe that we have overlooked. With the capabilities of the James Webb Space Telescope, researchers are now able to study these galaxies in unprecedented detail, looking for clues that might reveal how they formed and whether they truly lack dark matter or if some other hidden factor is at play. So, where does this leave us? Are DF2 and DF4 the cracks in the foundation of modern physics, signaling that our understanding of the cosmos is flawed? Or are they just rare exceptions that can be explained within our existing models? The answer is not yet clear, but what is certain is that these galaxies have opened one of the biggest mysteries in astrophysics. If we can solve this puzzle, we might not only uncover the true nature of dark matter but also gain a deeper understanding of the fundamental forces that shape the universe. Until then, the mystery remains, leaving us with more questions than answers, and a reminder that no matter how much we think we know, the cosmos always has surprises waiting for us just beyond the edge of the known universe. If DF2 and DF4 truly lack dark matter, then their very existence forces us to confront an unsettling possibility. Have we been fundamentally wrong about how the universe works? Dark matter has been the backbone of modern cosmology for nearly a century, serving as the unseen glue that holds galaxies together and the driving force behind large-scale cosmic structures. Yet, if galaxies can exist without it, then dark matter might not be as essential as we thought. Or perhaps, our understanding of it is far more limited than we ever imagined. One of the most perplexing aspects of these galaxies is their sheer improbability. According to our current models, dark matter was crucial in the early universe, providing the gravitational scaffolding necessary for gas to collapse and form galaxies in the first place. If DF2 and DF4 somehow formed without it, we must ask, what force allowed them to take shape? Normal matter alone should not have been able to do the job. This raises the tantalizing possibility that there are hidden forces or unknown physical processes at play that we have yet to discover. One idea gaining traction among researchers is that DF2 and DF4 could have been born from highly unusual cosmic conditions. Some scientists speculate that they may have formed in regions of space where dark matter was unusually diffuse or absent altogether. This could mean that dark matter is not as uniformly distributed across the cosmos as we previously assumed. If dark matter is more clumpy or fragmented than we thought, it could explain why some galaxies end up with more of it while others, like DF2 and DF4, end up with almost none. But this explanation comes with its own challenges. If dark matter is indeed unevenly distributed, then our entire understanding of cosmic structure formation might need to be rewritten. The large-scale web of the universe, with its vast filaments of dark matter connecting galaxies and galaxy clusters, might not be as continuous as we believed. This could mean that many more dark matter-free galaxies exist, hidden across the cosmos, waiting to be discovered. The implications of this are profound. If dark matter is not as universal as we thought, then many of the assumptions underlying modern cosmology could be flawed. For example, the lambda cold dark matter model, which has successfully explained a wide range of cosmic phenomena, might require significant revision. This model assumes that cold dark matter, which moves slowly and does not interact with normal matter except through gravity, is responsible for the formation of galaxies and large-scale structures. But if DF2 and DF4 exist without dark matter, then this model might not be the full story. Even more intriguingly, these galaxies might be pointing us toward an entirely new form of physics. Some researchers have suggested that DF2 and DF4 could be evidence of exotic forms of matter or energy that we have not yet detected. Perhaps there is another invisible force acting within these galaxies, one that mimics the gravitational effects of dark matter but operates in a completely different way. If this is the case, then our search for dark matter might need to expand beyond the traditional particle-based explanations that have dominated the field for decades. This leads to an even deeper question. Could these galaxies be the key to solving one of the greatest mysteries in physics, the true nature of gravity itself? Many physicists have speculated that our current understanding of gravity, based on Einstein's general relativity, might be incomplete. Alternative theories, such as modified Newtonian dynamics, MOND, and emergent gravity, propose that gravity behaves differently on cosmic scales than we currently assume. If DF2 and DF4 are stable without dark matter, then they could be providing the strongest evidence yet that gravity itself needs to be redefined. But while MOND offers an intriguing alternative, it comes with its own set of challenges. The theory struggles to explain certain cosmic observations, such as the distribution of galaxies and galaxy clusters and the patterns of the cosmic microwave background radiation. If MOND were the answer, then it should be able to explain all these phenomena consistently. But so far, it has not. This means that while DF2 and DF4 might hint at new physics, they do not necessarily confirm any specific alternative theory just yet. The search for more dark matter-free galaxies has now become a top priority for astronomers. If DF2 and DF4 are the only known examples, then they might simply be rare exceptions. But if more such galaxies are discovered, then we will be forced to reconsider everything we thought we knew about dark matter. With the power of telescopes like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory, scientists are scanning the universe for more anomalies like these, hoping to uncover whether DF2 and DF4 are unique or part of a much larger pattern. If we do find more dark matter-free galaxies, the next step will be to understand how they formed. Were they stripped of their dark matter by interactions with other galaxies? Did they form in an environment where dark matter was naturally absent? Or are they pointing us toward an entirely new form of matter that we have yet to discover? These questions remain open, and their answers could reshape the very foundation of astrophysics. Until we have more definitive answers, DF2 and DF4 remain as cosmic anomalies, mysterious outliers that challenge the very fabric of our understanding. Their existence forces us to question the assumptions we have taken for granted and pushes us toward new, uncharted frontiers of scientific discovery. Whether they ultimately confirm our theories, refine them, or force us to discard them altogether, one thing is certain: the universe still has secrets waiting to be uncovered, and dark matter-free galaxies might just be the key to unlocking one of the greatest mysteries of all time. The existence of dark matter-free galaxies challenges one of the most fundamental assumptions in astrophysics: that dark matter is the invisible scaffolding that holds galaxies together. If DF2 and DF4 truly lack dark matter, then either we have found an extraordinary exception to the rule, or we have completely misunderstood the role dark matter plays in the formation of galaxies. This realization sends shockwaves through modern cosmology because it suggests that our models, which have been carefully refined for decades, may be missing something critical. One of the biggest questions that arises from these galaxies is how they formed in the first place. According to the prevailing lambda-cold dark matter model, dark matter was essential in the early universe for pulling gas together, allowing the first galaxies to form. If DF2 and DF4 lack dark matter, then their very existence contradicts this idea. This means that either they formed through an entirely different process, or that dark matter behaves in a way we do not yet understand. scientists are now looking at different possibilities that could explain how such galaxies could have formed without dark matter's gravitational pull. One possibility is that DF2 and DF4 originally had dark matter but lost it due to interactions with other galaxies. Galaxies do not exist in isolation. They are part of a cosmic web of gravitational interactions, constantly colliding, merging, and stripping material from one another. It is possible that DF2 and DF4 were once normal galaxies, but had their dark matter stripped away by a violent interaction with a larger galaxy. This could have happened if they passed through a dense region of space where strong gravitational forces tore away their dark matter, leaving behind only the visible stars and gas. However, this explanation has problems. If these galaxies lost their dark matter through gravitational interactions, we would expect to see signs of disruption in their structure, such as distorted shapes, unusual motions of stars, or remnants of tidal interactions. But observations suggest that DF2 and DF4 appear surprisingly undisturbed. Their stars move in ways that suggest they have never been subject to the kind of extreme gravitational interactions that would be necessary to strip away dark matter. This raises another question. If their dark matter was removed, why do these galaxies still appear so normal? Another hypothesis is that DF2 and DF4 formed in a unique environment where dark matter was naturally absent. In most galaxies, dark matter is thought to have been present in the early universe, clumping together due to gravity and allowing normal matter to gather and form stars. But what if there are pockets of the universe where dark matter is less abundant or missing altogether? If DF2 and DF4 formed in such a region, they might have developed without dark matter from the very beginning. This could mean that dark matter is not as evenly distributed across the cosmos as we once thought. If true, this would have enormous implications. It would suggest that dark matter does not exist as a smooth, uniform halo around every galaxy, but instead forms in clumps or voids. This could help explain why we have struggled to directly detect dark matter. It may not be everywhere, but only in specific regions. This could also mean that there are many more dark matter-free galaxies out there, waiting to be discovered. Another, more radical, possibility is that DF2 and DF4 are pointing us toward a new form of physics. Some scientists believe that these galaxies could be evidence that our current understanding of gravity is incomplete. One alternative theory is called modified Newtonian dynamics, MOND, which suggests that gravity behaves differently on very large cosmic scales. According to MOND, the effects that we currently attribute to dark matter could actually be the result of an unknown property of gravity itself. If MOND is correct, then DF2 and DF4 might not actually be missing dark matter. Rather, their behavior could be explained by a different set of gravitational laws that we have not yet fully understood. However, MOND has its own challenges. While it can explain certain galactic observations, it struggles to explain large-scale cosmic structures, such as galaxy clusters and the cosmic microwave background radiation. If DF2 and DF4 are providing evidence for MOND, then the theory will need to be refined to account for other unexplained cosmic phenomena. A completely different line of thinking suggests that these galaxies could be evidence of a new kind of matter or force that we have not yet discovered. In physics, the search for new particles is ongoing, with many scientists looking for signs of exotic forms of matter beyond the standard model. It is possible that DF2 and DF4 are interacting with an unknown form of matter that mimics some properties of dark matter but behaves differently. This would mean that dark matter is not a single, uniform substance, but rather a collection of different phenomena that we have yet to fully map out. As astronomers continue to study these galaxies, new discoveries are being made. More dark matter-free galaxies are now being identified, suggesting that DF2 and DF4 are not unique anomalies but rather part of a larger population. The more of these galaxies we find, the harder it becomes to dismiss them as mere outliers. Each new discovery adds more weight to the argument that our understanding of dark matter is incomplete. With upcoming telescopes like the James Webb Space Telescope and the Vera C. Rubin Observatory, we will soon have the ability to detect even more of these mysterious galaxies. If we find hundreds, or even thousands, of dark matter-free galaxies, then we will have no choice but to reconsider everything we thought we knew about the universe. These galaxies could be the key to unlocking a new era of physics, revealing hidden forces, unknown particles, or even a completely new framework for understanding gravity and cosmic structure. But for now, DF2 and DF4 remain as cosmic anomalies, defying the standard model of the universe and challenging everything we thought we knew about dark matter. Whether they ultimately confirm a new theory, refine our existing models, or force us to rethink the very nature of reality, one thing is certain: the universe still holds mysteries far beyond our current understanding, and the search for answers is only just beginning. The discovery of DF2 and DF4 raises another major question. If these galaxies are truly dark matter-free, what does that mean for the role of dark matter in the rest of the universe? For decades, scientists have built models based on the assumption that dark matter is necessary for galaxies to form and stay together. If DF2 and DF4 can exist without it, does that mean dark matter is less important than we thought? Or does it mean that there is more than one way for galaxies to form? These questions don't just impact the study of these two galaxies. They shake the foundation of cosmology itself. One way to explore this mystery is to look at other galaxies and see if there are more out there like DF2 and DF4. If only a handful of dark matter-free galaxies exist, then maybe they are just rare exceptions caused by unusual cosmic circumstances. But if astronomers find many more of them, it could mean that dark matter isn't as universal as we thought. In recent years, more galaxies have been found that appear to have little or no dark matter, suggesting that DF2 and DF4 are not unique anomalies. For example, astronomers have identified other ultra-diffuse galaxies, UDGs, with unusual properties. Some of these galaxies seem to have much more dark matter than expected, while others have almost none. This raises an even bigger question. Why do some galaxies end up with an abundance of dark matter while others have almost none? If dark matter is supposed to be the invisible glue holding galaxies together, then why do some galaxies appear to function just fine without it? One hypothesis is that the distribution of dark matter might depend on the environment in which a galaxy forms. If a galaxy forms in a region with a lot of other galaxies, it might experience interactions that strip away or rearrange its dark matter. In contrast, a galaxy forming in a more isolated region might retain its dark matter halo. This could explain why some galaxies seem to have an excess of dark matter while others appear to lack it entirely. Another possibility is that dark matter interacts with itself or with normal matter in ways we don't fully understand. The leading theory today is that dark matter is cold, meaning it moves slowly and does not interact much with normal matter except through gravity. But what if that's not entirely true? If dark matter can interact with itself, it might be possible for it to be pulled away from certain galaxies, explaining why some galaxies appear to be missing it. This idea is particularly interesting because there have already been hints that dark matter might not be completely inert. Some studies of galaxy clusters suggest that dark matter might interact in subtle ways, creating effects that cannot be explained by gravity alone. If true, this could mean that DF2 and DF4 are not actually missing dark matter. They might simply be galaxies where dark matter has behaved in a way that we do not yet understand. One way to test this is to study the formation of dark matter-free galaxies in computer simulations. Scientists can create virtual universes and see if galaxies like DF2 and DF4 appear naturally under certain conditions. If they do, then we might have a better idea of how these galaxies formed. If they don't, then we will have to seriously rethink our models of galaxy formation. Some early simulations have suggested that dark matter-free galaxies might form when a young galaxy undergoes a major event, such as a close encounter with a larger galaxy or a burst of intense star formation. These events could push dark matter out of the galaxy, leaving behind only the visible stars and gas. However, the challenge is that these simulations have yet to produce galaxies that look exactly like DF2 and DF4. This means that either we are missing some key details in the simulations, or that something else is going on. Another approach is to look at the stars within these galaxies and see if they hold any clues. If DF2 and DF4 form differently from normal galaxies, then their stars might have unusual properties. By studying the chemical composition of these stars, scientists can learn about their history and determine whether these galaxies formed in a unique way. So far, studies of the stars in DF2 and DF4 have suggested that they are relatively old and lack large amounts of heavy elements, which might indicate that they formed very early in the history of the universe. This raises yet another intriguing possibility. Could dark matter-free galaxies be relics from an earlier time in the universe? If these galaxies formed in the very early universe, before dark matter had fully settled into its role in galaxy formation, then they might represent a snapshot of a time when galaxies were forming in a different way. If this is the case, then DF2 and DF4 might be among the oldest galaxies in existence, providing a rare glimpse into the conditions of the early cosmos. However, this explanation has its own challenges. If DF2 and DF4 are ancient relics, then we should expect to find more like them scattered throughout the universe. But so far, only a handful of such galaxies have been discovered. This suggests that whatever process created them was rare or only happened under very specific conditions. There is also the possibility that dark matter itself is more complex than we think. Some theories suggest that dark matter could come in different forms, just like normal matter is made up of different types of particles. If this is true, then DF2 and DF4 might be missing one kind of dark matter while still having another kind that we haven't detected yet. This would mean that our current methods of searching for dark matter are incomplete, and that we might need new tools to fully understand it. Another wild possibility is that DF2 and DF4 could be evidence for an alternative explanation of cosmic structure. Some physicists have proposed that gravity itself might work differently at large scales than it does on smaller scales. This idea, known as modified gravity, suggests that what we currently call dark matter might not be a physical substance at all, but rather a sign that our understanding of gravity is incomplete. If this idea is correct, then DF2 and DF4 could be the first direct proof that our theories of gravity need revision. Regardless of which explanation turns out to be correct, one thing is certain. DF2 and DF4 are forcing astronomers to rethink some of the most fundamental questions in cosmology. Are they anomalies? Or are they telling us something profound about the nature of the universe? Are they missing dark matter because it was stripped away, or because they formed without it? And what do they mean for our broader understanding of how galaxies and cosmic structures form? As new telescopes come online and more data is collected, astronomers will continue to search for more dark matter-free galaxies. If more of them are found, then we will need to seriously reconsider our theories about dark matter and galaxy formation. If, on the other hand, DF2 and DF4 turn out to be rare exceptions, then we will need to understand what makes them different from all other galaxies. Either way, the search for answers will lead to new discoveries and new questions, reminding us once again that the universe is far more mysterious than we ever imagined. If DF2 and DF4 are not anomalies, and more dark matter-free galaxies are discovered, this could radically change our understanding of the role of dark matter in the universe. It would mean that dark matter is not a fundamental requirement for galaxy formation, which contradicts decades of astrophysical models. If galaxies can exist without dark matter, we need to rethink why dark matter is present in so many others. What if dark matter is not the cosmic glue we thought it was? What if its role is more complex or conditional, dependent on circumstances we have yet to understand? The mere existence of galaxies without dark matter raises the possibility that dark matter is not as universal as once believed, or worse, that we may have misunderstood its very nature. One theory that attempts to explain these dark matter-free galaxies suggests that they could be the result of extreme gravitational interactions. Imagine a young galaxy forming in a crowded cluster, surrounded by massive neighboring galaxies exerting strong gravitational pulls. These forces could strip the forming galaxy of its dark matter before it has fully developed. This would leave behind a collection of stars and gas, but without the unseen mass that typically holds a galaxy together. This tidal stripping hypothesis is one of the leading explanations, but it has limitations. If DF2 and DF4 have lost their dark matter through interactions with other galaxies, we would expect to see clear signs of these interactions, like distorted shapes, stretched out stellar streams, or trails of leftover dark matter. However, no such evidence has been found. These galaxies look surprisingly undisturbed, which suggests their lack of dark matter may be an intrinsic feature rather than a result of external forces. Another possibility is that these galaxies formed in regions of space where dark matter was naturally scarce. Some cosmologists propose that dark matter is not evenly distributed across the universe but instead forms in clumps and filaments. If DF2 and DF4 happen to form in areas with very little dark matter, they may have simply developed differently than other galaxies. This could mean that dark matter is not a fundamental ingredient of galaxy formation but rather something that most galaxies acquire by chance, depending on where they form. If this theory is correct, then dark matter-free galaxies should be rare but not impossible to find. It also suggests that the distribution of dark matter in the universe is even more mysterious than we thought. Yet another explanation could lie in the nature of dark matter itself. Most current theories suggest that dark matter is made of slow-moving, weakly interacting particles that do not emit light. This is known as cold dark matter, and it explains why galaxies can hold onto their dark matter halos for billions of years. However, some scientists propose that dark matter might be more dynamic than we assume. If dark matter particles can interact with one another, they might be capable of escaping from certain galaxies under the right conditions. In this case, DF2 and DF4 might not be truly dark matter-free. They might have started with dark matter but later lost it due to some unknown interaction. This could mean that dark matter is not a single type of particle but rather a family of particles with different properties, some of which might be more prone to being stripped away. If dark matter can be separated from normal matter under certain conditions, this would have profound implications. It would mean that dark matter might behave differently in different environments, and that the way we detect it might need to change. Currently, dark matter is inferred based on gravitational effects, but what if there are aspects of dark matter that cannot be detected this way? What if we need entirely new tools to understand its true nature? Some physicists argue that the discovery of dark matter-free galaxies could even support alternative theories of gravity, such as modified Newtonian dynamics, MOND. MOND suggests that what we call dark matter is not a real substance but instead an indication that gravity behaves differently on cosmic scales. In this model, galaxies do not need dark matter to explain their motions. Rather, the force of gravity itself changes at large distances. If MOND is correct, then DF2 and DF4 could be important test cases. If these galaxies behave according to MOND's predictions without requiring dark matter, it could mean that our entire understanding of gravity needs to be rewritten. However, MOND remains a controversial theory, as it struggles to explain certain observations that dark matter models handle well. Regardless of the explanation, the existence of dark matter-free galaxies forces us to question everything we thought we knew about the universe. If dark matter is as essential as scientists believe, then how can galaxies exist without it? If dark matter is missing from these galaxies, where did it go? Is it possible that dark matter is not as fundamental as we assumed, or is it something we still do not fully understand? One way to answer these questions is to continue searching for more dark matter-free galaxies. If astronomers find dozens or even hundreds of them, it would suggest that they are not just rare oddities but rather an important part of cosmic evolution. If, on the other hand, DF2 and DF4 remain outliers, then we must understand what makes them unique. Either way, the search for answers will push the boundaries of modern astrophysics and force us to reconsider our understanding of the cosmos. As technology advances, new telescopes like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory will provide deeper insights into these enigmatic galaxies. These powerful instruments will allow astronomers to study DF2, DF4, and other potential dark matter-free galaxies in greater detail. By analyzing their stars, gas, and dynamics, scientists hope to uncover whether these galaxies truly formed without dark matter or if there is an unseen force at play. At the same time, particle physicists are working on experiments to directly detect dark matter and understand its properties. If we can confirm what dark matter is made of, we may be able to explain why some galaxies lack it. The Large Hadron Collider, underground dark matter detectors, and space-based observatories are all part of this effort. If dark matter particles are found and their properties studied, we might finally be able to explain the strange case of DF2 and DF4. Ultimately, the mystery of dark matter-free galaxies is not just about these two galaxies. It is about the fundamental nature of the universe itself. These galaxies challenge the very models that cosmologists have relied on for decades. They remind us that even in the 21st century, when we have mapped billions of stars and galaxies, the universe still holds secrets that defy our understanding. They force us to confront the limits of our knowledge and push us to ask deeper questions about the fabric of reality. Are DF2 and DF4 the key to unlocking the mystery of dark matter, or are they anomalies that defy explanation? Are they relics from an ancient cosmic era, or proof that our theories about galaxy formation need to be rewritten? As astronomers continue to investigate, one thing is certain: the cosmos is far more mysterious than we ever imagined. The answer to this puzzle could change everything we know about the universe, or it could open even greater mysteries we have yet to uncover. If DF2 and DF4 truly lack dark matter, then the implications extend far beyond these individual galaxies. The entire framework of how galaxies form, evolve, and interact with their surroundings would need to be revisited. Traditionally, dark matter has been considered the unseen foundation of galactic structures, influencing everything from the rotation of galaxies to the distribution of cosmic filaments that form the large-scale structure of the universe. Without dark matter, DF2 and DF4 raise a troubling question: is dark matter truly necessary for galaxy formation, or are there alternative processes at play that we have yet to understand? One of the biggest questions surrounding dark matter-free galaxies is whether they are truly lacking dark matter or if our methods of detecting dark matter are flawed. Currently, we infer the presence of dark matter by observing how galaxies rotate and how they interact gravitationally with their surroundings. In most galaxies, stars move at speeds that suggest there is much more mass present than what we can see. However, DF2 and DF4 appear to have mass distributions that align with only their visible matter. This suggests either that they genuinely lack dark matter or that dark matter interacts with them in a way we have not yet accounted for. If our understanding of dark matter detection is incomplete, then the implications could be even more far-reaching. It could mean that there are other forms of dark matter that do not behave the way we expect, or that dark matter can somehow become invisible under certain conditions. Some physicists have speculated about the possibility of self-interacting dark matter, which could explain why dark matter appears to be missing from certain galaxies while still existing in others. This theory suggests that dark matter particles may have the ability to interact with each other in complex ways, possibly even separating from galaxies under specific conditions. If this is the case, then DF2 and DF4 might not be truly dark matter-free but rather in a state where their dark matter has been redistributed or obscured from our view. Another possibility is that DF2 and DF4 are part of a class of galaxies that formed through a completely different mechanism than we currently understand. Most galaxies are believed to form through the gradual accumulation of matter, with dark matter serving as the gravitational foundation that pulls in gas and dust to create stars. However, what if some galaxies can form without the need for dark matter? If this is true, then our current theories of galaxy formation would need to be rewritten to include multiple pathways for galactic evolution. One potential explanation for the existence of dark matter-free galaxies involves the idea that these galaxies were once part of a larger system that somehow lost its dark matter. Imagine a galaxy forming in a region of space where it initially had dark matter but later experienced an event that stripped it away. This could have been caused by a violent interaction with another galaxy, a massive collision, or even an encounter with a cosmic phenomenon we have yet to understand. If DF2 and DF4 were once part of a galaxy cluster where interactions stripped them of their dark matter, then they could represent a rare case of galaxies that survived such an event but were left without their original dark matter halos. Some astronomers have proposed that these galaxies could have formed in regions of space where dark matter is naturally scarce. The cosmic web, the large-scale structure of the universe, is composed of vast filaments of dark matter that connect galaxies and galaxy clusters. However, there are also large voids in this cosmic web, regions where matter is sparse and the gravitational influence of dark matter is weaker. If DF2 and DF4 formed in one of these voids, they might have naturally developed without significant amounts of dark matter. This would mean that dark matter is not a requirement for galaxy formation but rather a common feature that most galaxies acquire through their placement within the cosmic web. Yet another possibility is that dark matter is not actually a separate substance at all but rather an effect of modified gravity. This idea, often referred to as modified Newtonian dynamics, MOND, suggests that gravity behaves differently at large scales than it does at small scales. If MOND is correct, then the reason most galaxies appear to have dark matter could be because gravity works differently in those environments, not because an unseen substance is present. DF2 and DF4 could be key pieces of evidence in this debate. If their motions match the predictions of MOND rather than the predictions of dark matter models, it could lend support to the idea that dark matter is not a real entity but rather an illusion created by our incomplete understanding of gravity. At the same time, there are other anomalies in the universe that might be connected to the mystery of dark matter-free galaxies. For example, there are galaxies with far more dark matter than expected, where the visible matter accounts for only a tiny fraction of the total mass. If dark matter can be missing from some galaxies and overconcentrated in others, then this suggests that dark matter does not distribute itself evenly across the cosmos. It raises the possibility that dark matter is dynamic, capable of moving between galaxies under certain conditions, or even forming structures that we have yet to identify. One of the biggest challenges in solving the mystery of dark matter-free galaxies is the need for better observational data. While DF2 and DF4 have been studied using some of the most advanced telescopes available, future missions will provide even more detailed insights. The James Webb Space Telescope, JWST, with its ability to observe faint objects at high resolutions, could reveal hidden details about these galaxy structures, star populations, and interactions with their surroundings. Similarly, the Vera C. Rubin Observatory, which will conduct a massive survey of the night sky, may discover additional dark matter-free galaxies, helping us understand whether DF2 and DF4 are unique or part of a larger pattern. There are also ongoing efforts to directly detect dark matter in laboratory experiments. If dark matter is a particle, then it should occasionally interact with normal matter, even if only weakly. Experiments like those conducted in underground dark matter detectors aim to capture these rare interactions and provide clues about the nature of dark matter. If such experiments confirm the existence of dark matter and reveal its properties, they could help explain why DF2 and DF4 appear to be missing it. Conversely, if these experiments continue to fail in detecting dark matter, it could suggest that our entire understanding of the universe's mass distribution is incomplete, lending support to alternative theories like MOND. Regardless of the ultimate explanation, the existence of dark matter-free galaxies challenges our current understanding of the cosmos. If these galaxies truly lack dark matter, then we must ask why they exist and what their presence means for our broader understanding of the universe. If, on the other hand, they do contain dark matter in some hidden form, then we need to rethink how dark matter behaves and how we detect it. Either way, DF2 and DF4 represent one of the most intriguing astrophysical mysteries of our time, reminding us that the universe is far more complex than we ever imagined. The search for answers will continue, with astronomers, physicists, and cosmologists all working to unravel the puzzle of these galaxies. As new data emerges, we may find that these galaxies hold the key to understanding dark matter, or we may discover that the true answer lies in an even greater mystery that has yet to be uncovered. The cosmos is full of surprises, and as we explore deeper into its vast and uncharted territories, we are reminded that for every question we answer, countless more await discovery. If DF2 and DF4 truly lack dark matter, it forces us to reconsider a fundamental assumption, that all galaxies require dark matter to form and remain stable. This assumption has been a cornerstone of cosmology for decades. If these galaxies defy that rule, then either dark matter is not as universal as we thought, or our understanding of galaxy formation is incomplete. One possibility is that these galaxies formed under unique conditions where dark matter played little or no role. If that's the case, what are those conditions? Could other galaxies have formed the same way? And if so, how many more are out there that we haven't yet identified? The biggest challenge in studying these galaxies is confirming that they truly lack dark matter. Our main method for detecting dark matter is by observing the motion of stars and gas within galaxies. If a galaxy rotates faster than expected based on its visible matter, we infer the presence of dark matter. However, if DF2 and DF4 appear to behave as if they have no extra mass beyond their visible stars, it could mean they lack dark matter, or it could mean we are missing something in how we interpret their motion. Could there be hidden interactions at play that mimic the effect of dark matter while actually redistributing it in ways we don't yet understand? One theory suggests that these galaxies lost their dark matter through gravitational interactions with larger nearby galaxies. If DF2 and DF4 were once part of a galaxy cluster, they could have been stripped of their dark matter by tidal forces exerted by larger galaxies. These forces can pull stars and gas away from smaller galaxies, and in some cases, they might also separate dark matter from the visible components. If this process occurred in DF2 and DF4, it could mean that their dark matter still exists somewhere nearby but is no longer gravitationally bound to them. Another intriguing idea is that dark matter itself might behave in ways we haven't anticipated. If dark matter can be influenced by unknown forces or interactions, it might be able to detach from certain galaxies under the right conditions. Some physicists have proposed that dark matter could have self-repelling properties, which could explain why it seems to be missing in some places but abundant in others. If dark matter can separate from normal matter under specific conditions, then DF2 and DF4 might be the first known examples of this process in action. These possibilities bring up even deeper questions about the nature of dark matter. One of the biggest mysteries in physics is why we haven't yet detected dark matter directly. If dark matter is a particle, as many theories suggest, it should occasionally interact with normal matter in ways we can measure. Yet, decades of experiments have failed to provide definitive proof of dark matter's existence. If dark matter is real but remains undetected, then it must be interacting in ways that are incredibly weak or unusual. On the other hand, if dark matter doesn't exist at all, then we need an entirely new explanation for the missing mass in the universe. An alternative explanation for DF2 and DF4 is that dark matter is not a separate entity, but rather an effect of gravity behaving differently on cosmic scales. This idea, known as modified Newtonian dynamics, MOND, suggests that at extremely low accelerations, such as those found in deep space, gravity operates in ways that deviate from standard physics. If MOND is correct, then what we call dark matter could simply be a misinterpretation of how gravity works at large distances. DF2 and DF4 could be crucial test cases for this theory. If their motion can be explained by MOND rather than dark matter, then it could mean that our entire understanding of cosmic forces needs to be revised. Another perplexing question is whether dark matter-free galaxies are rare or common. So far, DF2 and DF4 are among the only galaxies that appear to lack dark matter, but this could be because they are the first to be studied in detail. If astronomers find more galaxies like them, it could mean that dark matter-free galaxies are a natural part of the universe, rather than anomalies. On the other hand, if no other examples are found, then DF2 and DF4 might be unique, which would make understanding them even more critical. Future telescopes will play a major role in solving this mystery. The James Webb Space Telescope, JWST, will allow astronomers to study these galaxies with unprecedented detail, analyzing their structure, star formation history, and interactions with their environment. Additionally, upcoming surveys from the Vera C. Rubin Observatory will scan the night sky for more examples of dark matter-free galaxies. If more are found, it could provide critical clues about what makes them different from normal galaxies. One of the most exciting aspects of this mystery is that it connects to fundamental questions about the universe itself. If dark matter-free galaxies exist, then they could help us understand how matter is distributed across the cosmos. They could also provide insights into the early universe. After all, if these galaxies formed without dark matter, then perhaps similar processes occurred in the past. Could there have been an era when galaxies commonly formed without dark matter, only for most of them to later acquire it? If so, what does that mean for our understanding of cosmic history? Ultimately, the mystery of DF2 and DF4 is not just about two galaxies. it's about the very fabric of the universe. Whether they truly lack dark matter, lost it through some unknown process, or reveal a flaw in our understanding of gravity, these galaxies challenge everything we thought we knew about the cosmos. They force us to question our assumptions, reconsider our theories, and push the boundaries of what is possible. In the coming years, as astronomers gather more data and refine their models, we may finally uncover the truth about these galaxies, and in doing so, reshape our entire understanding of the universe. If DF2 and DF4 truly lack dark matter, then one of the biggest implications is that dark matter may not be as universally necessary for galaxy formation as we once thought. For decades, astronomers have believed that dark matter serves as the gravitational scaffolding around which galaxies form. In standard cosmological models, clouds of hydrogen gas collapse into galaxies because of the gravitational pull of surrounding dark matter. If DF2 and DF4 formed without dark matter, then how did they come into existence? Did they form in a completely different way that defies our current understanding, or did they originally contain dark matter but somehow lost it? One possibility is that DF2 and DF4 were originally part of a larger galaxy cluster and lost their dark matter through extreme gravitational interactions. This process, called tidal stripping, occurs when a smaller galaxy passes close to a larger galaxy or a dense cluster of galaxies. The intense gravitational forces from the larger system can strip away the outer layers of the smaller galaxy, pulling away gas, stars, and possibly dark matter. If DF2 and DF4 experience such an event, it could explain why they lack dark matter while still maintaining their structure. However, the problem with this theory is that dark matter is thought to be more gravitationally sticky than normal matter, meaning it should be harder to remove. If DF2 and DF4 lost their dark matter while retaining their stars, it suggests something unusual about the way dark matter interacts, or fails to interact, with normal matter. Another hypothesis suggests that dark matter-free galaxies might be remnants of violent galactic collisions. When two galaxies merge, their dark matter halos are expected to combine as well, forming an even larger dark matter-dominated structure. However, in rare cases, if the interaction is particularly chaotic, the dark matter might be flung away while the remaining stars settle into a new configuration. If DF2 and DF4 are the byproducts of such a process, they could represent a rare but natural outcome of galaxy collisions. The challenge is proving whether such an event actually happened in their past. Some researchers have even speculated that DF2 and DF4 could provide evidence for an alternative theory of gravity, such as modified Newtonian dynamics, MOND. According to MOND, the apparent effects of dark matter might not be caused by an unseen substance, but rather by a modification of how gravity behaves at very low accelerations. If MOND is correct, then DF2 and DF4 might simply be following different gravitational rules than expected. However, MOND has struggled to explain certain large-scale cosmic structures, and most astronomers still favor the dark matter hypothesis. But if more galaxies like DF2 and DF4 are found, it could lend credibility to the idea that our understanding of gravity itself needs revision. Another fascinating possibility is that dark matter may not be a single type of particle but rather a complex, multi-component substance with properties we don't yet understand. If dark matter comes in different forms, some of which can more easily detach from galaxies under certain conditions, then DF2 and DF4 might be examples of galaxies that lost a specific type of dark matter while retaining another. This idea is highly speculative but could explain why these galaxies appear to behave so differently from most others. The biggest challenge in solving this mystery is gathering more observational evidence. Current telescopes can only provide limited details about the structure and motion of DF2 and DF4. However, new instruments like the James Webb Space Telescope, JWST, and the upcoming Vera-C Rubin Observatory will allow astronomers to study these galaxies with much greater precision. By analyzing their star populations, gas content, and overall motion, scientists hope to determine whether these galaxies are truly devoid of dark matter, or if some unknown factor is making them appear that way. One key area of investigation is whether DF2 and DF4 are unique, or if other similar galaxies exist. If more dark matter-free galaxies are discovered, it would suggest that they are not anomalies but rather a natural, albeit rare, type of galaxy. This would have profound implications for our understanding of the universe, potentially forcing cosmologists to rethink how galaxies form and evolve. On the other hand, if DF2 and DF4 remain the only known examples, then understanding what makes them different becomes even more critical. Another question is whether dark matter-free galaxies could have implications for our broader understanding of the universe. If some galaxies can exist without dark matter, it might mean that the total amount of dark matter in the universe is lower than we previously estimated. This, in turn, could affect our calculations about the expansion of the universe and the ultimate fate of cosmic structures. It could also provide new clues about the mysterious nature of dark energy, the force thought to be driving the accelerated expansion of the universe. At the heart of this mystery is the fundamental question: what is dark matter, and how does it shape the cosmos? The standard model of cosmology suggests that dark matter makes up about 27% of the universe's total mass energy content, while normal matter, the atoms and molecules that make up stars, planets, and people, comprises just 5%. If dark matter is truly essential for galaxy formation, then DF2 and DF4 should not exist. Yet they do. This contradiction suggests that either dark matter behaves in ways we don't yet understand, or that an entirely new explanation is needed. The search for answers is ongoing, and each new discovery adds another piece to the puzzle. Future surveys will continue scanning the sky for more dark matter-free galaxies, while particle physicists work to detect dark matter directly in underground laboratories. If dark matter turns out to be something far stranger than we ever imagined, then DF2 and DF4 might be the first galaxies to hint at a deeper truth about the universe. Whatever the answer, one thing is certain: the mystery of these galaxies is not just about dark matter, it's about the fundamental forces that shape reality itself. If DF2 and DF4 are truly devoid of dark matter, they force us to reconsider our most fundamental assumptions about galaxy formation. For decades, astronomers have worked under the belief that dark matter acts as an invisible framework, binding galaxies together and influencing their structure. The standard model suggests that galaxies form within dark matter halos, where the gravitational pull of this unseen substance helps condense normal matter into stars and planets. Yet, these two galaxies challenge that assumption. If they exist without dark matter, how did they form? And if dark matter isn't necessary for a galaxy's existence, what does that mean for our broader understanding of the cosmos? One possible explanation is that DF2 and DF4 lost their dark matter through extreme gravitational interactions. When galaxies interact, their gravitational fields can pull material away from each other, distorting their shapes and redistributing mass. In theory, if DF2 and DF4 once contained dark matter, they might have lost it through a process known as tidal stripping. This occurs when a smaller galaxy passes near a much larger galaxy or galaxy cluster, and the intense gravitational forces tear away the weaker material. But this explanation has problems. Dark matter is thought to be less affected by gravitational stripping than ordinary matter, meaning it should be harder to remove. If these galaxies were stripped of their dark matter while still retaining their stars, then dark matter may not behave as we currently believe. Another theory suggests that DF2 and DF4 are the remnants of galactic collisions. When two galaxies collide, their dark matter halos are expected to merge, but in rare cases, the process might not be so orderly. If the collision was particularly violent, dark matter could have been scattered or displaced, leaving behind a system of stars without its usual invisible mass. But if this were the case, we should expect to find more galaxies like DF2 and DF4 as remnants of similar interactions. The fact that such galaxies are rare suggests that whatever caused them to lose dark matter must be an unusual event rather than a common one. Some scientists have proposed that DF2 and DF4 provide evidence for alternative physics, specifically, modified Newtonian dynamics, MON. This theory suggests that the effects attributed to dark matter might actually be due to a modification of gravity at very low accelerations. If MON were correct, then DF2 and DF4 could be examples of galaxies where this modified gravity behaves differently than expected. However, MON struggles to explain other large-scale cosmic structures, and it lacks direct experimental support. The vast majority of astronomers still consider dark matter to be the most likely explanation for the missing mass in the universe. A more speculative idea is that dark matter might not be a single, uniform type of substance but a more complex entity with different forms. If dark matter can exist in multiple states, some of which can detach from galaxies under certain conditions, then DF2 and DF4 might be examples of galaxies that lost one form of dark matter while retaining another. This concept is purely hypothetical, but it could help explain why these galaxies behave differently from most others. The search for answers is far from over. Future observations, particularly those from the James Webb Space Telescope, JWST, and the upcoming Vera C. Rubin Observatory, will provide more data on the structure and motion of DF2 and DF4. If astronomers can measure the movements of more stars within these galaxies, they can determine whether the lack of dark matter is real or just an illusion caused by observational limitations. Additionally, if more galaxies like DF2 and DF4 are discovered, it would indicate that dark matter-free galaxies are a natural part of cosmic evolution rather than rare anomalies. Another key question is whether dark matter-free galaxies could impact our broader understanding of the universe. If some galaxies can form without dark matter, it could mean that our estimates of the total amount of dark matter in the cosmos are too high. This, in turn, could affect our models of cosmic expansion and the fate of the universe itself. If dark matter plays a smaller role than previously thought, it might change how we understand the structure of large-scale cosmic formations, such as galaxy clusters and superclusters. At its core, the mystery of DF2 and DF4 is a challenge to our understanding of the most fundamental forces in the universe. If dark matter is real, why do these galaxies exist without it? If dark matter is not real, what is causing the strange behavior observed in other galaxies? The answers to these questions could redefine astrophysics. For now, DF2 and DF4 remain anomalies, but anomalies are often where the greatest scientific breakthroughs begin. If these galaxies are part of a larger pattern, they may force us to rewrite the rules of how galaxies form, how dark matter interacts with normal matter, and possibly even how gravity itself works. The ongoing search for more dark matter-free galaxies will be crucial in determining whether these two galaxies are outliers or the first clues to a much deeper cosmic truth. Whatever the answer turns out to be, one thing is certain: DF2 and DF4 are not just ordinary galaxies. They are cosmic puzzles that force us to question everything we thought we knew about the universe. And as astronomers continue to search the skies, who knows what other mysteries might be waiting to be discovered? The implications of dark matter-free galaxies stretch far beyond DF2 and DF4. If they truly lack dark matter, then our understanding of cosmic evolution might be missing a crucial piece. Galaxies have long been considered the building blocks of the universe. But if some of them form in radically different ways than we previously thought, then we may need to rethink the fundamental forces shaping cosmic structures. Could it be that dark matter plays only a secondary role in galaxy formation rather than a primary one? Or are DF2 and DF4 unique cosmic accidents, their existence the result of extraordinary conditions that we have yet to understand? One of the most pressing questions is whether DF2 and DF4 are the only examples of dark matter-free galaxies or if there are more waiting to be discovered. If these galaxies are incredibly rare, then they might be exceptions rather than rules, meaning they could have formed through unique events like galactic collisions or extreme tidal interactions. But if more galaxies like them are found, then it could suggest that our theories about dark matter and galaxy formation are incomplete. Scientists are already scanning the skies for more examples, and future telescopes will provide even deeper insights into the true nature of these strange objects. The very existence of DF2 and DF4 challenges the idea that dark matter is necessary for a galaxy to remain stable. Traditionally, dark matter is thought to act as the glue that holds galaxies together, preventing their stars from flying apart due to their high rotational speeds. But if DF2 and DF4 are truly devoid of dark matter and still maintain a coherent structure, then either dark matter isn't as essential as we thought, or these galaxies are somehow being stabilized in a way we don't yet understand. One possible explanation is that these galaxies are held together by an alternative force, perhaps interactions between normal matter that we haven't fully explored. Some researchers suggest that star formation itself might play a role in maintaining galactic stability, as the energy and radiation from massive stars could influence the dynamics of a galaxy in unexpected ways. However, this doesn't fully explain how these galaxies remain intact without the added gravitational pull of dark matter. Another strange feature of DF2 and DF4 is their unusually sparse appearance. Compared to other galaxies of similar mass, their stars are spread out much more thinly, giving them an almost ghostly, diffuse quality. This could mean that they formed in an environment very different from most galaxies, or that they experienced some kind of event that caused them to expand and lose density. One possibility is that they were once more typical galaxies but were stretched apart by gravitational interactions with other, more massive galaxies. If so, this stretching might have played a role in removing their dark matter, leaving behind only the visible stars. The idea that dark matter could be stripped away from a galaxy is not entirely new, but it does raise significant questions. Most models suggest that dark matter is far less affected by gravitational interactions than normal matter, meaning that it should be harder to remove. If DF2 and DF4 truly lost their dark matter through some stripping process, then it could indicate that dark matter behaves differently than we thought. Perhaps it interacts with itself in ways we haven't yet observed, or maybe it isn't as strongly bound to galaxies as we previously believed. Some scientists have even proposed that DF2 and DF4 could be evidence of exotic forms of dark matter, such as self-interacting dark matter. Unlike traditional dark matter, which is thought to only interact with normal matter through gravity, self-interacting dark matter could exert forces on itself, allowing it to be displaced or redistributed under certain conditions. If this theory is correct, then DF2 and DF4 might not be truly dark matter-free but instead might have experienced a process that separated their dark matter from their visible matter. The ongoing debate over these galaxies highlights one of the biggest mysteries in modern astrophysics. We still don't fully understand what dark matter is. Despite decades of research, no direct evidence for dark matter has been found. We infer its existence based on its gravitational effects, but all attempts to detect it through experiments have so far come up empty. If DF2 and DF4 are truly lacking dark matter, they could provide a crucial clue about its nature, whether it's real, whether it behaves differently than we thought, or whether our entire understanding of gravity needs to be reconsidered. Some physicists have even suggested that these galaxies could be evidence that dark matter doesn't exist at all. If we find enough examples of galaxies that don't require dark matter to remain stable, then it might be time to consider alternative theories, such as modifications to the laws of gravity. The idea that gravity behaves differently at large scales isn't new, but it has never gained mainstream acceptance because dark matter so effectively explains many cosmic phenomena. However, if more galaxies like DF2 and DF4 are found, then these alternative theories might gain new support. The discovery of dark matter-free galaxies is also significant because it forces us to reconsider how galaxies form in the first place. If dark matter is not a necessary ingredient, then there might be multiple pathways to galaxy formation, some involving dark matter and others not. This could mean that the universe is far more diverse than we previously thought, with galaxies existing in a wide range of configurations that challenge our existing models. As astronomers continue to study DF2 and DF4, they will be looking for more clues about their origins. One key piece of evidence will come from studying their surrounding environments. If these galaxies formed in isolation, then their lack of dark matter might be due to an unusual formation process. But if they are found near larger galaxies or galaxy clusters, then their dark matter could have been stripped away by gravitational interactions. Future observations will also focus on measuring the motions of individual stars within these galaxies. By tracking how these stars move, scientists can determine whether an unseen mass, such as dark matter, is affecting their orbits. If the stars move exactly as expected based on visible matter alone, then it will further confirm that these galaxies lack dark matter. But if unexpected motions are detected, then it might mean that some form of dark matter is still present, just behaving in an unusual way. The next generation of telescopes, such as the Vera C. Rubin Observatory, will provide even more detailed observations of ultra-diffuse galaxies like DF2 and DF4. These telescopes will be capable of detecting fainter objects and measuring the properties of stars in unprecedented detail. If they find more galaxies with little to no dark matter, then we may have to completely rethink our models of galaxy formation. Another exciting possibility is that the study of dark matter-free galaxies could lead to new insights into the nature of dark matter itself. If dark matter does exist, but certain galaxies can lose it, then understanding how that process occurs might help us unlock its secrets. Could dark matter be more complex than we thought? Could it have different forms, some of which interact more strongly with normal matter than others? These are the kinds of questions that scientists are now beginning to explore. Regardless of what the final answer turns out to be, the discovery of DF2 and DF4 represents a major turning point in our understanding of the universe. If they are truly devoid of dark matter, then they may be the first examples of a completely new type of galaxy. If they challenge our existing theories of gravity, they could force physicists to rethink the very laws of the cosmos. And if they help us better understand dark matter, then they could lead to one of the greatest scientific breakthroughs of our time. But perhaps the most exciting aspect of this mystery is that it is still unfolding. The universe is vast, and we have only just begun to explore its many secrets. If DF2 and DF4 are just the beginning, then who knows what else we might find? Could there be entire clusters of galaxies that lack dark matter? Could there be galaxies that contain only dark matter, with no stars at all? The possibilities are endless, and as technology advances, our ability to uncover these cosmic mysteries will only grow stronger. For now, DF2 and DF4 remain enigmas, strange, ethereal galaxies that challenge everything we thought we knew about the universe. But as we continue to explore, study, and question, one thing is certain: the search for answers will lead us to even greater discoveries. And perhaps, in the process, we will finally unlock the deepest secrets of the cosmos itself. The search for more dark matter-free galaxies has become one of the most intriguing pursuits in modern astronomy. DF2 and DF4 have already shaken our understanding of how galaxies form and evolve, but the real breakthrough will come if astronomers can confirm that such galaxies are not anomalies, but part of a broader cosmic pattern. Scientists are now using the most advanced telescopes available to scan the universe for other ultra-diffuse galaxies that may lack dark matter. If more examples are found, it could provide powerful evidence that galaxies can form and survive without the mysterious gravitational glue that we once thought was essential. One of the key methods astronomers are using to find more galaxies like DF2 and DF4 is deep sky imaging combined with precise velocity measurements of stars and globular clusters. By studying how these celestial objects move, scientists can determine the gravitational influence in a galaxy and assess whether there is any unseen mass holding it together. If more galaxies are found where the movement of stars perfectly aligns with the visible mass alone, it could indicate that entire families of galaxies exist without dark matter. This would force scientists to completely reconsider how galaxies form, and potentially rewrite fundamental theories of cosmology. However, there's still a lingering possibility that DF2 and DF4 do have dark matter, but that it behaves in an unexpected way. One idea is that these galaxies could be composed of a form of dark matter that is more diffuse and spread out than usual, making it difficult to detect through traditional methods. Some physicists propose that if dark matter consists of extremely low-mass particles that don't clump together in the same way as normal matter, it might explain why some galaxies appear to lack it entirely. There is also an alternative explanation involving a process called tidal interactions. In this scenario, DF2 and DF4 may have once contained dark matter, but powerful gravitational forces from nearby galaxies stripped it away. This could have occurred over billions of years through repeated encounters with larger galaxies or clusters. If this is the case, then DF2 and DF4 may not have formed without dark matter, but rather lost it at some point in their history. This would mean that dark matter isn't necessarily required for galaxy formation, but it would still be crucial for maintaining stability in most cases. Some researchers have also suggested that DF2 and DF4 could be evidence for new physics beyond the standard model of cosmology. If dark matter doesn't exist in these galaxies but is present everywhere else, it could mean that the laws of gravity operate differently under certain conditions. One of the leading alternative theories to dark matter is called modified Newtonian dynamics, MOND. This theory suggests that gravity itself changes at very low accelerations, which could explain why most galaxies appear to be influenced by an unseen force, while DF2 and DF4 are not. If MOND or another alternative theory turns out to be correct, it would mean that our understanding of gravity needs to be completely reworked. Another fascinating question that arises from these dark matter-free galaxies is whether they might be connected to another cosmic mystery, dark energy. While dark matter is believed to provide the extra gravity needed to hold galaxies together, dark energy is thought to be responsible for the accelerating expansion of the universe. Some scientists speculate that dark matter and dark energy could be two sides of the same phenomenon. If that's the case, then the existence of galaxies without dark matter might provide new clues about the true nature of the mysterious forces governing the cosmos. The implications of this discovery go beyond just astrophysics. If DF2 and DF4 are part of a new class of galaxies, then their existence could influence other scientific fields, such as particle physics and cosmology. If dark matter is real but can be removed from galaxies under specific conditions, then physicists may need to rethink how dark matter particles interact with normal matter. This could lead to the development of new theories about the fundamental structure of the universe. At the same time, if DF2 and DF4 are not truly devoid of dark matter but instead contain a form that we cannot currently detect, then this could push researchers toward new experimental approaches to finding dark matter. For decades, physicists have been trying to detect dark matter particles using underground laboratories and particle accelerators, but all attempts have so far come up empty. If dark matter is hiding in a different form than previously expected, it may require an entirely new way of searching for it. The mystery of these galaxies also has significant implications for the study of cosmic evolution. If dark matter-free galaxies exist, then it means that the universe has a much broader range of galaxy types than we previously thought. This suggests that galaxy formation might not be a one-size-fits-all process, but instead a dynamic and diverse phenomenon that can take multiple paths. If astronomers can figure out how these galaxies formed, it may lead to a deeper understanding of how the first galaxies emerged after the Big Bang. Furthermore, studying dark matter-free galaxies might help scientists determine whether dark matter itself is a fundamental component of the universe, or just an effect caused by something even more exotic. There are some radical theories that suggest dark matter might not actually be a particle at all, but rather a manifestation of extra dimensions, or even a byproduct of quantum gravity. If galaxies can exist without dark matter, then it could support the idea that what we perceive as dark matter is actually the result of unknown physics beyond our current understanding. The search for more examples of these galaxies is still in its early stages, but astronomers are already planning major observational campaigns to look for additional cases. Some of the upcoming telescopes, like the James Webb Space Telescope and the Extremely Large Telescope, will have the ability to observe faint, diffuse galaxies in unprecedented detail. If they find more galaxies like DF2 and DF4, it will confirm that these aren't just rare exceptions but rather a real and significant aspect of the universe's structure. Another approach scientists are using is studying galaxy clusters to see if similar phenomena occur on a larger scale. If entire clusters of galaxies are found with unusually low amounts of dark matter, it could provide strong evidence that dark matter behaves differently than we expect. On the other hand, if these galaxies remain isolated cases, then they might have formed through highly specific and rare conditions that are unlikely to be repeated elsewhere. Ultimately, the question of whether DF2 and DF4 are truly dark matter-free remains one of the greatest mysteries in modern astrophysics. If they are, then they could be the first glimpses of an entirely new class of galaxies that challenge our understanding of the universe. If they are not, then studying them could still reveal new insights about how dark matter behaves and interacts with normal matter. As our observational techniques improve, we will likely uncover even more surprises about the universe. Whether DF2 and DF4 end up rewriting the laws of physics or simply adding an interesting wrinkle to our current models, they have already sparked a scientific debate that could lead to profound discoveries. And perhaps, in the process of studying these enigmatic galaxies, we will finally come closer to solving one of the biggest cosmic puzzles of all time, the true nature of dark matter. The implications of dark matter-free galaxies extend far beyond just altering our view of galaxy formation. If these galaxies truly exist without dark matter, it forces us to ask a much deeper question: what if dark matter itself is not what we think it is? For decades, the prevailing view has been that dark matter is a yet undiscovered type of particle that interacts gravitationally but not electromagnetically, making it invisible to our telescopes. However, the existence of galaxies without dark matter might challenge this view, suggesting that dark matter is either something much more complex or, in some cases, not necessary at all. One of the most radical ideas that emerges from this discovery is that our understanding of gravity might be flawed. For years, some physicists have proposed alternative theories of gravity, such as modified Newtonian dynamics, MOND, which suggest that what we perceive as dark matter is actually the result of a change in how gravity behaves at very large scales or extremely low accelerations. If DF2 and DF4 lack dark matter but still function as stable galaxies, it could be indirect evidence that gravity does not behave the way we think it does. MOND proposes that at very low gravitational accelerations, such as those found in the outer edges of galaxies, the force of gravity does not follow Newton's laws in the same way it does in our solar system. This could explain why most galaxies appear to have more gravitational pull than their visible mass suggests. Because gravity itself is behaving differently, rather than there being an invisible substance providing extra mass. The existence of dark matter-free galaxies could provide crucial tests for MOND, because if they truly lack dark matter, then MOND would predict that their internal motions should follow a different set of gravitational rules than galaxies with dark matter. However, there are problems with this idea. MOND struggles to explain the distribution of large-scale cosmic structures, such as galaxy clusters, and it fails to account for some of the patterns seen in the cosmic microwave background radiation, which is the afterglow of the Big Bang. This is why most physicists still favor the dark matter hypothesis over modified gravity theories. But the discovery of dark matter-free galaxies could force scientists to revisit these alternative ideas and search for new ways to explain how the universe works. Another theory that could be relevant to these galaxies is the idea that dark matter is not a particle at all, but rather a fundamental property of spacetime itself. Some physicists suggest that dark matter could be the result of quantum effects at cosmic scales, meaning that it could emerge naturally from the fabric of the universe without requiring actual particles. If this were true, then some regions of the universe could have different amounts of this emergent, dark matter, explaining why some galaxies appear to lack it entirely. Then there's the possibility that DF2 and DF4 are not actually dark matter-free, but instead contain a form of dark matter that behaves in an unusual way. Traditionally, dark matter is thought to be cold, meaning it moves relatively slowly and clumps together under gravity. But what if dark matter in these galaxies is instead warm, or self-interacting, meaning it spreads out and does not cluster in the same way? Some models of dark matter propose that certain types of galaxies could have dark matter that is more diffuse, making it harder to detect through traditional means. If DF2 and DF4 contain such a form of dark matter, then it could explain why their stars move as if they are governed only by visible matter. Astronomers are currently conducting follow-up studies to confirm whether DF2 and DF4 truly lack dark matter. If further observations confirm this, then scientists will need to find a new explanation for how galaxies can exist without it. One possibility is that these galaxies formed in an environment where dark matter was naturally scarce. This could happen in the presence of strong cosmic winds from nearby galaxies, which might have stripped away any dark matter before the galaxies could fully form. Alternatively, they might have formed in a way that prevented dark matter from accumulating in the first place, such as through a unique interaction with the early universe's cosmic web. If more dark matter-free galaxies are found, it could provide a major breakthrough in our understanding of the structure of the universe. One of the key goals of future telescopes, such as the Vera C. Rubin Observatory, is to map out thousands of ultra-diffuse galaxies and determine whether DF2 and DF4 are unique or part of a larger pattern. If a significant number of these galaxies are found, it could indicate that galaxy formation is far more diverse than we ever imagined. At the same time, if DF2 and DF4 remain isolated cases, then it could mean that something very unusual happened to them specifically. Perhaps they were part of a larger galaxy that lost most of its mass due to a violent gravitational interaction, leaving behind only the visible stars while the dark matter was pulled away. Or maybe they formed under extreme conditions that prevented dark matter from binding to them. The ultimate question remains, if some galaxies can exist without dark matter, then does this mean that dark matter is not essential to the universe after all? For decades, dark matter has been considered one of the fundamental building blocks of cosmic structure, but these galaxies might be telling us that it's not the full story. Perhaps there are multiple ways for galaxies to form, some with dark matter and some without. If that's the case, then dark matter might be just one piece of a much larger cosmic puzzle that we have yet to fully understand. The next few years will be crucial in determining what these dark matter-free galaxies truly mean for physics and astronomy. With more observations, better simulations, and new theories being tested, we may soon find ourselves facing a scientific revolution that changes everything we thought we knew about the universe. Whether it turns out that these galaxies are evidence for a new form of matter, a new law of gravity, or simply a strange cosmic accident, one thing is certain. The mystery of dark matter-free galaxies is one of the most exciting questions in modern astrophysics, and the search for answers is only just beginning. If DF2 and DF4 truly lack dark matter, it could mean that our assumptions about how galaxies form and evolve need to be revised. One of the core ideas in modern cosmology is that galaxies form inside halos of dark matter, which act like scaffolding that gathers ordinary matter together. This is based on observation showing that most galaxies have much more gravity than can be accounted for by their visible stars and gas. However, if galaxies can form without dark matter, then it raises the question, how did DF2 and DF4 come to exist in the first place? One possibility is that these galaxies formed in a region of space where dark matter was simply absent. The large-scale structure of the universe is shaped by a cosmic web of filaments, vast interconnected structures of dark matter and galaxies. If DF2 and DF4 formed in a rare part of space where dark matter is unusually sparse, it could explain why they have so little of it. However, this would be an extraordinary coincidence, as almost all galaxies studied so far have been found to contain significant amounts of dark matter. Another theory suggests that DF2 and DF4 originally formed like normal galaxies with dark matter, but later lost it due to interactions with other galaxies. If a larger galaxy passed nearby, its gravitational forces could have stripped away the dark matter while leaving the visible stars behind. This is known as tidal stripping, and it has been observed in some galaxy clusters where smaller galaxies are stretched out and disrupted by the gravity of their larger neighbors. However, DF2 and DF4 are located in relatively isolated regions, making this explanation less likely unless a past interaction occurred that we have not yet detected. Some researchers have proposed that DF2 and DF4 might contain dark matter, but in a form that does not behave like the cold dark matter we expect. For example, if dark matter is self-interacting, meaning that it interacts with itself through forces other than gravity, it could cause the dark matter to spread out and become less concentrated. This could make it appear as though the galaxy lacks dark matter when in reality, it is just distributed differently. If this is the case, then DF2 and DF4 might provide evidence for a new type of dark matter that behaves in unexpected ways. There is also the possibility that our measurements are wrong. Astronomers determine the presence of dark matter by measuring the motion of stars and gas within a galaxy. If the stars in DF2 and DF4 are moving in a way that suggests little to no dark matter, it could be due to an observational bias or an error in our models of galactic motion. Some scientists have suggested that these galaxies might not actually be as dark matter-free as they seem, and that better observations could reveal hidden dark matter that we have simply overlooked. One of the biggest challenges in confirming whether DF2 and DF4 truly lack dark matter is the difficulty of studying such faint galaxies. Ultra-diffuse galaxies are incredibly difficult to observe because their stars are spread out over a large area, making them almost invisible against the background of space. Future telescopes, such as the upcoming James Webb Space Telescope and the Vera C. Rubin Observatory, will provide much more detailed data on these galaxies, allowing scientists to determine their true nature. If more dark matter-free galaxies are discovered, it would suggest that these objects are not just rare outliers, but rather an important piece of the puzzle in understanding how galaxies form. This could lead to the development of new models of galaxy formation that allow for both dark matter-rich and dark matter-poor galaxies to exist. Some scientists have even suggested that if enough of these galaxies are found, they could be used to test competing theories of gravity, such as MOND, which predicts that the behavior of galaxies should be different in the absence of dark matter. The debate over dark matter-free galaxies is far from settled, and it is likely to continue for years to come. As astronomers gather more data, they may find that these galaxies are not truly dark matter-free but instead contain dark matter in an unexpected form. Alternatively, if they are confirmed to lack dark matter, it could force a fundamental revision of our understanding of the universe. Whether DF2 and DF4 turn out to be cosmic anomalies or the key to a major scientific breakthrough, they have already changed the way we think about galaxy formation. The next few years will be crucial in resolving this mystery. If astronomers discover more galaxies like DF2 and DF4, it will strengthen the case that dark matter-free galaxies are a real phenomenon that needs to be explained. If they remain isolated cases, then scientists will need to consider whether they are simply unusual exceptions to the rule. In either case, these galaxies challenge our assumptions about how the universe works and provide a new frontier for exploration in astrophysics. Ultimately, the search for answers about dark matter-free galaxies is part of a much larger quest to understand the true nature of the cosmos. Whether dark matter is a particle, a modification of gravity, or something even stranger, these galaxies remind us that the universe is full of surprises. As new telescopes come online and new discoveries are made, we may find that DF2 and DF4 are just the beginning of a revolution in our understanding of the hidden forces shaping the universe. The implications of dark matter-free galaxies stretch far beyond just these two objects. If DF2 and DF4 are not anomalies but instead represent a broader class of galaxies, then the entire framework of modern cosmology could require adjustment. Dark matter has long been considered a cornerstone of the universe's structure, influencing everything from the formation of galaxies to the movement of galaxy clusters. If galaxies can form and exist without dark matter, then perhaps our models overestimate its role. Or maybe dark matter behaves in ways we have not yet considered. One potential avenue of exploration involves the study of galactic interactions. If DF2 and DF4 were once part of a larger system that experienced a violent gravitational event, then their missing dark matter might not be missing at all. It might have been stolen. When galaxies collide or pass close to each other, their gravitational interactions can strip away matter, including dark matter. In theory, DF2 and DF4 might have once contained dark matter, but a past encounter with another massive object could have disrupted their structure, leaving behind only the luminous matter. However, the problem with this explanation is that we should be able to detect traces of this lost dark matter nearby. If dark matter is truly missing, it raises the question of whether it was ever there to begin with. This leads to another radical possibility. Could dark matter itself be a fluid-like substance that can be displaced under the right conditions? Some theoretical physicists have suggested that dark matter may not be a collection of individual particles but instead something more akin to a field or a fluid that interacts with normal matter in complex ways. If this is true, then the conditions that lead to dark matter-free galaxies might involve an unknown mechanism that allows dark matter to separate from normal matter under specific circumstances. This would mean that DF2 and DF4 are not just rare oddities but rather windows into a new aspect of physics that we do not yet understand. Another major implication of dark matter-free galaxies is their potential impact on alternative gravity theories. One of the biggest competitors to dark matter is a theory known as modified Newtonian dynamics, MOND. MOND suggests that instead of there being missing dark matter, gravity itself behaves differently on large cosmic scales. According to MOND, the reason galaxies appear to have extra mass is because gravity operates differently in low acceleration environments, effectively mimicking the effects of dark matter. However, For Mon to be correct, all galaxies should behave as if they have dark matter, even if no dark matter is present. The discovery of DF2 and DF4, which behave as if they lack dark matter entirely, directly challenges Mond, because these galaxies show weaker gravity than expected. If more galaxies like these are found, it could further undermine Mond and reinforce the idea that dark matter is indeed a real substance. But what if there is another explanation that we haven't even considered? Some researchers have suggested that DF2 and DF4 might not actually be dark matter-free at all, but rather that our observations are missing something crucial. Astronomers infer the presence of dark matter by measuring the movement of stars in a galaxy, but these measurements are incredibly difficult to make, especially in ultra-diffuse galaxies like DF2 and DF4. If there is an error in the way we are interpreting these observations, then the apparent lack of dark matter might be an illusion. Future telescopes with better sensitivity might reveal that DF2 and DF4 do contain dark matter, but in a form that is distributed differently than what we expect. Some scientists have also considered the possibility that DF2 and DF4 are the result of an entirely new formation process that we have not seen before. Most galaxies are thought to form within dark matter halos, but what if there is another way? Perhaps under certain conditions, it is possible for gas and stars to collapse into a galaxy-like structure without the help of dark matter. If such a process exists, then DF2 and DF4 might be the first confirmed examples of a completely different type of galaxy, one that forms through mechanisms we have yet to understand. There is also the question of whether DF2 and DF4 are truly unique, or if we are simply at the beginning of a larger discovery. If astronomers begin finding more dark matter-free galaxies, it will indicate that these objects are not just rare accidents but rather a fundamental part of the universe. This would mean that whatever process created them is relatively common, and that our models of galaxy formation need to account for the existence of galaxies without dark matter. However, if DF2 and DF4 remain the only known examples, then it suggests that something highly unusual happened to these particular galaxies, and understanding what that was could provide new insights into cosmic evolution. Ultimately, the search for dark matter-free galaxies is not just about these two objects. It is about testing the very foundations of what we think we know about the universe. If dark matter is truly necessary for galaxy formation, then DF2 and DF4 should not exist. The fact that they do exist means that either our understanding of dark matter is incomplete, or that there is another explanation waiting to be discovered. With upcoming advancements in observational technology, such as the Vera-C, Rubin Observatory and the next generation of space telescopes, we may soon get answers to some of these questions. For now, DF2 and DF4 remain anomalies, strange cosmic objects that refuse to fit into our current models. Whether they are proof of a fundamental flaw in our theories or simply outliers in an otherwise well-understood universe is something that astronomers will continue to investigate. As more data is gathered, we may one day look back at these galaxies as the key to unraveling one of the greatest mysteries in modern astrophysics. But until then, they stand as reminders that the universe is still full of surprises, waiting to be uncovered. The mystery of dark matter-free galaxies challenges some of the most fundamental assumptions we have about the universe. For decades, the dominant model of cosmology has been based on the idea that dark matter plays a critical role in shaping the formation and evolution of galaxies. If galaxies like DF2 and DF4 genuinely lack dark matter, it means we either need to reconsider the properties of dark matter itself, or explore entirely new ways that galaxies can form. The implications extend far beyond astrophysics. They touch on the very fabric of reality itself. One of the strangest aspects of dark matter-free galaxies is that they contradict the standard model of cosmology, known as the lambda cold dark matter model. This model suggests that galaxies form within dark matter halos, with normal matter, like gas and stars, falling into these halos and eventually forming galaxies. Without dark matter, the gravitational pull of these halos should be too weak to hold galaxies together. So how did DF2 and DF4 form in the first place? If they lack dark matter, then something must have allowed their stars to cluster and remain bound despite the absence of the invisible mass that supposedly holds galaxies together. One possible explanation is that these galaxies formed in an environment where dark matter was somehow stripped away. Some researchers have suggested that they might have formed in a region of space where interactions with another massive galaxy or cluster of galaxies pulled away their dark matter. This could have happened through tidal interactions, where gravitational forces from a nearby massive object literally stretched the dark matter away from the galaxy, leaving behind only the visible stars. However, this theory has problems. If dark matter was stripped away, then we should be able to find traces of it nearby, but so far, no evidence of this missing dark matter has been found. Another possibility is that DF2 and DF4 are actually illusions, galaxies that only appear to lack dark matter because of the way we are observing them. Some astronomers have proposed that measurement errors or observational limitations might be causing us to misinterpret their motion. When astronomers determine the mass of a galaxy, they usually measure the motion of its stars. If the stars are moving slowly, it suggests the galaxy has little to no dark matter. But what if our measurements are flawed? What if we are underestimating the speed of these stars? Or if some unknown factor is affecting their motion? If this is the case, then DF2 and DF4 might not actually be dark matter free, but rather just difficult to measure accurately. But perhaps the most intriguing possibility is that DF2 and DF4 are proof that dark matter is not as universal as we once thought. If dark matter can be present in some galaxies but absent in others, it might mean that dark matter is not a fundamental ingredient of galaxy formation. Instead, it might be something that forms under specific conditions. This would force us to rethink how galaxies form and evolve over time. It could also open the door to entirely new models of physics, ones that do not rely on dark matter at all. This idea brings us to one of the most controversial theories in physics, modified Newtonian dynamics, MON. MON suggests that there is no dark matter at all, and that what we call dark matter effects are actually the result of gravity behaving differently in certain conditions. According to MON, galaxies appear to have extra mass because gravity changes at extremely low accelerations. But here's the problem. MON predicts that all galaxies should exhibit these modified gravitational effects, regardless of whether or not they contain dark matter. The discovery of DF2 and DF4 actually contradicts MON, because these galaxies behave exactly as they should if dark matter is absent. If MON were correct, then even dark matter-free galaxies should still show stronger gravitational effects, but they don't. This puts MON in an awkward position, as it suggests that the theory may not be correct after all. If dark matter-free galaxies continue to be found, it could provide new insight into what dark matter actually is. Currently, scientists believe dark matter is some kind of exotic particle, one that does not interact with normal matter except through gravity. But what if dark matter is something more complex? What if it has properties that allow it to be present in some galaxies but not in others? This would suggest that dark matter might not be a single, uniform substance, but rather a collection of different particles or forces that behave differently in different environments. There is also the possibility that dark matter interacts with itself in ways we do not yet understand. Some scientists have proposed that dark matter might experience self-interactions, meaning it can clump together or separate under certain conditions. If DF2 and DF4 are truly dark matter-free, then it might mean that dark matter has been pushed away by some unknown force. This would require us to reconsider how dark matter behaves on a fundamental level and might lead to the discovery of entirely new physical laws. One of the biggest challenges in solving the mystery of dark matter-free galaxies is the need for more data. So far, only 2 confirmed dark matter-free galaxies have been discovered, and while this is intriguing, it is not enough to rewrite the laws of physics just yet. Scientists are now searching for more examples of such galaxies, using powerful telescopes to scan the universe for similar objects. If more galaxies like DF2 and DF4 are found, it will suggest that dark matter-free galaxies are a common phenomenon, and that we need to adjust our theories to account for them. But if no other examples are found, then it could mean that DF2 and DF4 are rare exceptions, perhaps the result of some unusual cosmic event that we have yet to understand. Advancements in telescope technology will be crucial in solving this puzzle. Future observatories, such as the Vera C, Rubin Observatory, the James Webb Space Telescope, and upcoming next-generation radio telescopes will provide astronomers with unprecedented detail about the structure of galaxies. These instruments will allow scientists to probe deeper into the nature of dark matter and determine whether DF2 and DF4 are unique anomalies or part of a larger pattern. Ultimately, the mystery of dark matter-free galaxies is one of the most exciting puzzles in modern astrophysics. It challenges our assumptions about how galaxies form, how gravity works, and what dark matter really is. Whether these galaxies are the result of unseen interactions, measurement errors, or new physics entirely, they are forcing scientists to question everything they thought they knew about the cosmos. And in the process, they are bringing us closer to uncovering the true nature of one of the universe's greatest mysteries. If dark matter-free galaxies like DF2 and DF4 are real and not observational errors, then we have to consider the implications for our current understanding of cosmology. One major issue is that the standard model of galaxy formation relies on dark matter to explain why galaxies hold together. The gravity from visible matter alone isn't strong enough to prevent galaxies from dispersing. Without dark matter, the structure of these galaxies is puzzling. What mechanism is keeping them intact? And if they formed without dark matter, does that mean other galaxies could form in unexpected ways too? One possibility is that we are looking at galaxies that formed in an environment fundamentally different from what we typically observe. Perhaps in certain conditions, galaxies can form in ways that do not require dark matter, or dark matter can be expelled from a galaxy after it has already formed. Some scientists have suggested that interactions with nearby galaxies might have stripped DF2 and DF4 of their dark matter, leaving behind only the visible stars. This idea aligns with what we see in galaxy clusters, where individual galaxies sometimes lose material due to gravitational interactions with their surroundings. However, if dark matter was stripped away, it should still be present somewhere nearby, but no such evidence has been found. This raises another question: if dark matter was removed, where did it go? Another challenge is explaining the motion of stars within these galaxies. In most galaxies, the speed of stars remains relatively constant even as you move farther from the center. This is one of the main pieces of evidence for dark matter, because without it, outer stars should move much more slowly. But in DF2 and DF4, stars move at exactly the speeds predicted by the visible mass alone. This is why scientists believe these galaxies lack dark matter. However, this also contradicts alternative theories like modified Newtonian dynamics, MOND, which predicts that even without dark matter, galaxies should still show strange gravitational effects. The fact that DF2 and DF4 do not show these effects is a major problem for MOND supporters. If dark matter-free galaxies exist, then we need to reconsider how dark matter behaves. One radical idea is that dark matter might not be as uniform as we assume. Instead of being a single type of particle spread evenly throughout the universe, it might exist in clumps or behave differently in certain regions. This could mean that dark matter has complex interactions that we have yet to understand. There could be factors that allow dark matter to detach from normal matter in rare cases, leading to galaxies that contain little to no dark matter at all. Another possibility is that what we call dark matter is not a single thing, but rather a set of different physical phenomena. Some scientists have proposed that dark matter could be a mix of different particles, including hypothetical particles like axions, sterile neutrinos, or even modifications to gravity itself. If this is the case, then some galaxies might end up forming in ways that do not require dark matter at all. This would mean that our current models of galaxy formation need serious revision. Astronomers are now searching for more examples of dark matter-free galaxies to determine whether DF2 and DF4 are truly unique or part of a broader phenomenon. If more such galaxies are found, it will suggest that dark matter-free galaxies are not rare flukes but a real and significant category of galaxies. However, if no other examples are discovered, then it could mean that DF2 and DF4 are the result of some unknown, highly unusual process. In either case, these galaxies challenge the assumptions that have shaped cosmology for decades. Future telescopes will help provide more answers. The James Webb Space Telescope, for instance, is capable of observing distant galaxies in extreme detail, allowing scientists to measure their motion and structure more precisely than ever before. The Vera C. Rubin Observatory, which will conduct large-scale sky surveys, may also help identify additional examples of galaxies that lack dark matter. By gathering more data, astronomers hope to determine whether dark matter-free galaxies are common, how they form, and whether they force us to rethink our understanding of dark matter. The discovery of dark matter-free galaxies is a reminder that the universe is far more complex than we often assume. Every time we think we have a solid understanding of how things work, nature surprises us with something unexpected. If galaxies can exist without dark matter, then what else are we missing? Could there be even more exotic types of galaxies out there? Could we be wrong about dark matter itself? These questions highlight just how much we still have to learn about the cosmos. Ultimately, dark matter-free galaxies may either reinforce our existing understanding of dark matter or force a revolution in physics. If we can explain them using known physics, it will strengthen our understanding of galaxy formation. But if they remain mysterious, then they could point us toward new physics, perhaps even a new fundamental force or an entirely new understanding of gravity itself. In the coming years, as technology advances and more discoveries are made, we may finally get closer to unraveling this cosmic mystery. If dark matter-free galaxies are real, then their existence forces us to ask a profound question: how much of our understanding of the universe depends on dark matter, and what happens if that foundation is weaker than we thought? For decades, dark matter has been the invisible glue that explains why galaxies hold together, why they spin the way they do, and why large-scale structures in the universe form as they do. But if galaxies can form without it, then perhaps dark matter is not as fundamental as we assumed. Or perhaps it is not the full story. One major issue with the discovery of dark matter-free galaxies is that they challenge the lambda-cold dark matter model, which is the standard model of cosmology. According to this model, dark matter is the dominant form of matter in the universe, accounting for about 85% of all matter. It is believed to play a crucial role in the formation of galaxies by providing additional gravitational pull, allowing gas and dust to clump together and form stars. If galaxies like DF2 and DF4 truly lack dark matter, then this raises serious questions about whether the lambda-cold dark matter model is missing something important. One potential explanation is that dark matter is not distributed as evenly as we thought. Instead of being a smooth and uniform component of galaxies, it might behave in a more dynamic and complex way. Some researchers have proposed that dark matter could be self-interacting, meaning that under certain conditions, it might be able to clump together, separate, or even be expelled from a galaxy entirely. If true, this would mean that dark matter behaves more like a fluid with unique properties rather than a simple, invisible mass. Another possibility is that dark matter interacts with normal matter in ways that we have not yet observed. It has long been assumed that dark matter only interacts with normal matter through gravity, and not through any other forces. But what if, under certain circumstances, dark matter can be repelled or influenced by processes we don't yet understand? If galaxies can shed their dark matter, this suggests that dark matter is not as passive as we thought, and there might be mechanisms that can manipulate its presence within galaxies. One radical alternative is that what we perceive as dark matter is not a substance at all, but rather a sign that our understanding of gravity is incomplete. Some physicists have proposed modified Newtonian dynamics, MOND, a theory that suggests that gravity behaves differently at very large scales, eliminating the need for dark matter. However, MOND has struggled to explain many of the observed properties of galaxies and galaxy clusters. The strange thing about DF2 and DF4 is that they do not fit into the MOND framework either, because MOND still predicts that there should be some unexplained gravitational effects even if dark matter isn't present. The fact that these galaxies behave exactly as expected based on visible matter alone is a major problem for MOND, just as much as it is for lambda-cold dark matter. To truly determine what is happening with dark matter-free galaxies, scientists need more data. Observations of other galaxies could help determine whether DF2 and DF4 are unique, or if there are many galaxies like them. If dozens or hundreds of dark matter-free galaxies are discovered, then it would suggest that dark matter behaves in ways we do not yet understand. On the other hand, if DF2 and DF4 remain outliers, then their existence might be due to a rare and specific process rather than a fundamental flaw in our theories. One of the biggest challenges in studying dark matter-free galaxies is that they are difficult to detect. Since dark matter does not emit light, it is usually inferred by observing the way galaxies rotate, or how they interact with other objects. But if a galaxy lacks dark matter, then its stars and gas alone must be used to study its properties. This makes it more challenging to find and confirm these galaxies, especially because telescopes must be extremely precise to measure the small differences in velocity that indicate whether dark matter is present or not. As future telescopes become more advanced, we may be able to get a clearer picture of what is happening. The James Webb Space Telescope, JWST, is already providing new insights into galaxy formation, and upcoming observatories like the Vera C. Rubin Observatory will conduct massive sky surveys that could uncover more unusual galaxies. These telescopes could help determine whether dark matter-free galaxies are common and whether they form in a predictable way. If dark matter-free galaxies turn out to be a real phenomenon, then their existence could help us refine or even redefine our understanding of the universe. They might reveal new properties of dark matter, suggest modifications to our current theories, or even provide evidence for completely new physics. Until then, they remain one of the most intriguing mysteries of modern astronomy, an unexpected challenge to one of the biggest assumptions in cosmology. The search for more dark matter-free galaxies is now one of the most exciting pursuits in modern astrophysics. If DF2 and DF4 are not unique, then how many such galaxies could exist? Could they be a rare cosmic anomaly? Or are they part of a larger pattern that we have simply overlooked? If these galaxies turn out to be common, then our understanding of galaxy formation will need to be completely rewritten. And if they remain isolated cases, then we need to explain what rare conditions led to their formation. One key question is how these galaxies came to exist in the first place. Most galaxies are believed to form within dark matter halos, with the invisible mass acting as a gravitational scaffold that allows gas and dust to clump together, eventually forming stars. But if DF2 and DF4 truly lack dark matter, then they either formed in a way that does not require dark matter, or they somehow lost their dark matter after formation. If they formed without dark matter, this suggests that dark matter is not always necessary for galaxy formation, an idea that directly contradicts the standard model of cosmology. If they lost their dark matter, then we need to figure out how that process occurred and whether it could happen to other galaxies. One hypothesis is that dark matter could be stripped from galaxies through gravitational interactions. This process, known as tidal stripping, occurs when a smaller galaxy passes near a larger galaxy or a massive galaxy cluster. The strong gravitational forces from the larger object can pull material away from the smaller galaxy, potentially removing its dark matter while leaving behind the stars and gas. However, there is no clear evidence that DF2 and DF4 have undergone such an interaction. There are no obvious signs that they have passed through a massive cluster, and there is no nearby structure that could have stripped away their dark matter. Another possibility is that dark matter itself behaves differently than we expect. One idea is that dark matter might be self-interacting, meaning that under certain conditions, it could clump together, separate, or be expelled from a galaxy entirely. Some scientists have proposed that dark matter could form structures similar to normal matter, with dark matter clouds, or streams, that move independently of galaxies. If this is the case, then perhaps DF2 and DF4 were once surrounded by dark matter, but some unknown process caused the dark matter to drift away or be ejected. A more extreme idea is that dark matter could be linked to some unknown force that allows it to decouple from normal matter under specific conditions. If true, this would mean that our understanding of fundamental physics is incomplete. Dark matter has long been assumed to interact only through gravity, but what if it can also interact in ways that we have not yet observed? If dark matter can be removed from galaxies by forces other than gravity, then we need to rethink everything we know about its role in the universe. There is also the possibility that these galaxies are not truly dark matter-free, but instead contain an unusual form of dark matter that does not behave in the expected way. Some researchers have proposed that dark matter could exist in multiple forms, with different types of dark matter particles that interact in complex ways. If DF2 and DF4 contain a type of dark matter that does not produce the same gravitational effects as ordinary dark matter, then it could be present without being detected using current methods. One major challenge in confirming the existence of dark matter-free galaxies is that our observations are still limited by current technology. While the measurements of DF2 and DF4 suggest that they lack dark matter, these measurements could be affected by unseen factors such as faint, undetected mass or errors in the distance calculations. If future observations show that these galaxies do contain dark matter after all, then the mystery will be resolved. But if they continue to appear dark matter-free, then the mystery deepens. This is where new telescopes will play a crucial role. The James Webb Space Telescope, JWST, is already revolutionizing our understanding of the cosmos by providing detailed images of distant galaxies, and it could help confirm whether DF2 and DF4 truly lack dark matter. The upcoming Vera C. Rubin Observatory will conduct large-scale sky surveys that could reveal additional examples of galaxies with little or no dark matter. If astronomers can find more galaxies like DF2 and DF4, then they can begin to piece together a pattern and determine whether these galaxies share a common origin. The question of dark matter-free galaxies ties into the larger mystery of dark matter itself. For decades, dark matter has been a central pillar of modern cosmology, explaining everything from galaxy formation to the large-scale structure of the universe. But if dark matter is not as fundamental as we thought, then we may need to rethink one of the biggest assumptions in physics. Could it be that dark matter is only one piece of a larger puzzle? Could we be missing an even deeper layer of reality, one that explains both the presence and absence of dark matter in galaxies? The answers to these questions could reshape our understanding of the universe. If dark matter-free galaxies exist, then they could provide crucial clues about the nature of dark matter, its role in galaxy formation, and the fundamental laws of physics. They might point us toward new physics, revealing forces or particles that we have not yet discovered. Or they might force us to modify our current theories, leading to a more refined model of how galaxies form and evolve. Whatever the outcome, the search for dark matter-free galaxies is one of the most exciting frontiers in modern astronomy. As new data comes in and our understanding of the cosmos deepens, we may finally unlock the secrets of these strange galaxies, and in doing so, gain new insights into the very fabric of the universe itself. The implications of dark matter-free galaxies stretch far beyond individual cosmic anomalies. If galaxies like DF2 and DF4 exist, then they challenge the most fundamental assumptions of astrophysics. The standard model of cosmology, often called the lambda cold dark matter model, relies on dark matter as the invisible glue that holds galaxies together. If some galaxies can exist without dark matter, then we must ask, is dark matter truly essential, or have we misunderstood its role all along? One possibility is that dark matter-free galaxies could provide direct evidence for alternative gravity theories. Some physicists have long speculated that dark matter might not be a form of unseen matter, but rather a sign that our understanding of gravity is incomplete. One of the most popular alternatives is modified Newtonian dynamics, MOND, which proposes that gravity behaves differently at extremely low accelerations. In MOND, galaxies do not need dark matter to stay together, because gravity itself changes at large cosmic scales. If DF2 and DF4 lack dark matter yet remain stable, this could support MOND or a related theory, suggesting that the universe operates under a different set of gravitational laws than we currently assume. However, there are problems with this explanation. MOND works well for explaining the rotation curves of spiral galaxies, where stars orbit at unexpectedly high speeds, but it struggles to account for large-scale cosmic structures such as galaxy clusters. Additionally, MOND would predict a certain level of gravitational effects even in galaxies like DF2 and DF4, yet observations still show an extreme absence of dark matter. This means that if MOND is correct, it may still need to be revised or expanded to account for galaxies like these. If dark matter does exist but is absent in certain galaxies, then we must explain why. One hypothesis is that dark matter may have been expelled from DF2 and DF4 by a violent cosmic event. One possible mechanism is RAM pressure stripping. where a galaxy moves through a dense intergalactic medium, losing its gas and possibly even its dark matter in the process. However, this process is not well understood, and it is unclear if it could remove dark matter while leaving the galaxy's stars intact. Another theory is that DF2 and DF4 formed in an environment where dark matter was never present. This would imply that dark matter is not evenly distributed across the universe, but rather exists in patches or structures that influence galaxy formation. If this is the case, then the existence of dark matter-free galaxies could help us map out the large-scale structure of dark matter itself. By studying these galaxies, we could uncover new details about how dark matter clusters and moves through the universe. One of the most exciting possibilities is that dark matter-free galaxies could be a clue to the very nature of dark matter itself. If dark matter is not just one type of particle, but instead a collection of different particles with varying properties, then it could behave in ways we do not yet understand. Some versions of dark matter theories propose that it may have its own interactions, meaning that under certain conditions, dark matter could be pulled away from galaxies or even form its own separate structures. If this is true, then studying galaxies like DF2 and DF4 could help us unlock the deeper physics behind dark matter. There is also the possibility that our observations of DF2 and DF4 are incomplete. The measurements showing that they lack dark matter rely on specific assumptions about how their stars move. If there are hidden sources of mass, such as faint, unseen objects or diffuse matter that we have not detected, then the galaxies may still contain dark matter, just in a form we have yet to recognize. This is why future observations will be critical in confirming or refuting the existence of dark matter-free galaxies. New telescopes and advanced observational techniques could provide the breakthrough we need. The James Webb Space Telescope, JWST, has already begun revealing new details about distant galaxies, and future surveys by the Vera C. Rubin Observatory could uncover more galaxies with similar properties. By studying additional candidates, astronomers can determine whether DF2 and DF4 are rare exceptions or part of a larger pattern. If dark matter-free galaxies turn out to be common, then we will need to rethink how galaxies form in the first place. This could lead to groundbreaking new physics, revealing either a previously unknown aspect of gravity or a more complex nature of dark matter. If these galaxies remain rare anomalies, then they still hold valuable clues about the extreme conditions that can affect dark matter distribution. Either way, studying them will bring us closer to understanding the true nature of the universe. Ultimately, the mystery of dark matter-free galaxies is not just about these specific objects, it is about the fundamental nature of reality itself. Whether they reveal new physics, confirm existing theories, or challenge our deepest assumptions, they represent one of the most intriguing questions in modern astrophysics. As technology advances and our observational capabilities improve, we may soon have the answers we seek. Until then, these galaxies remain cosmic enigmas, waiting to reveal their secrets. The discovery of dark matter-free galaxies like DF2 and DF4 forces us to confront some of the biggest questions in astrophysics. If these galaxies truly exist without dark matter, what does that mean for the rest of the universe? Is dark matter actually necessary for galaxy formation, or are we missing some key detail about how galaxies come together? Could it be that dark matter is not as universal as we once thought, or is something strange happening in these specific cases? These questions have enormous implications for our understanding of the cosmos, and answering them could change everything we think we know about the universe. One of the most important steps in solving this mystery is confirming whether these galaxies are truly devoid of dark matter. Astronomers rely on several methods to detect dark matter, and one of the main techniques is measuring the movement of stars and gas within galaxies. Normally, when scientists study a galaxy, they expect to see a difference between the visible mass, such as stars and gas, and the actual gravitational effects they observe. This discrepancy is what originally led scientists to propose the existence of dark matter in the first place. However, when researchers examined DF2 and DF4, they found that the stars were moving at speeds that could be fully explained by the visible matter alone. In other words, there was no extra unseen mass influencing their motion. This is a major anomaly because it contradicts decades of observations that suggest all galaxies contain significant amounts of dark matter. If DF2 and DF4 genuinely lack dark matter, one explanation is that they formed in an environment where dark matter was never present to begin with. This would challenge the idea that dark matter plays a fundamental role in galaxy formation. According to the standard model of cosmology, dark matter provides the gravitational scaffolding that allows galaxies to form and grow over billions of years. If some galaxies can form without it, then that suggests there may be multiple ways for galaxies to come together. It also raises the question, if these galaxies lack dark matter, how did they form at all? Did they emerge from an entirely different process than typical galaxies? If so, what conditions allowed that to happen? One possibility is that these galaxies formed through interactions with larger galaxies that strip them of their dark matter. If a galaxy passes through a region with intense gravitational forces, it could theoretically lose its dark matter while retaining its stars. However, this would require extremely specific conditions, and it's not yet clear if such an event could happen naturally on a large enough scale. If DF2 and DF4 were once normal galaxies with dark matter and later lost it, then we need to explain how and why this stripping process occurred. Was it due to an interaction with another galaxy? Could there be an unseen cosmic phenomenon responsible for separating dark matter from regular matter? Another theory is that DF2 and DF4 formed in a cosmic void, an area of the universe with extremely low density. In such an environment, the normal rules of galaxy formation might not apply, leading to the creation of unusual galaxies that lack dark matter. However, this raises another question. If these galaxies formed in a unique environment, why don't we see more examples like them? Are they rare exceptions? Or could we be missing other dark matter-free galaxies that exist but haven't been detected yet? Astronomers are now searching for more examples of galaxies like DF2 and DF4 to determine whether they are unique or part of a broader pattern. If additional dark matter-free galaxies are found, it could suggest that these objects are more common than we previously thought, forcing a re-evaluation of our models of galaxy formation. If, on the other hand, DF2 and DF4 remain rare anomalies, then we must figure out what makes them different from all other known galaxies. There's also the possibility that our observations are incomplete or misleading. Measuring the mass of galaxies is a complex process that involves assumptions about how light, mass, and gravity interact. If there are unseen factors influencing these galaxies, such as hidden sources of mass or unusual distributions of matter, then some scientists speculate that dark matter might not be a fundamental substance at all, but rather a side effect of a deeper, unknown force of nature. If this is true, then dark matter-free galaxies could provide critical evidence for alternative models of physics. For example, if gravity itself behaves differently on cosmic scales, then what we perceive as dark matter might actually be a manifestation of these altered gravitational laws. In this case, DF2 and DF4 could be key pieces of evidence pointing toward a new understanding of how gravity works across the universe. Ultimately, dark matter-free galaxies represent one of the biggest challenges to modern astrophysics. Whether they confirm existing theories, reveal new physics, or expose gaps in our current knowledge, they have the potential to reshape our understanding of the universe in profound ways. Scientists will continue studying these galaxies in hopes of unraveling their mysteries, but for now, they remain some of the most puzzling objects in the cosmos. The more we learn about them, the closer we may come to answering some of the biggest questions about the nature of reality itself. The search for answers about dark matter-free galaxies is far from over. Scientists are actively looking for more galaxies like DF2 and DF4 to determine whether these anomalies are rare exceptions or if they point to something fundamentally wrong with our understanding of the universe. If these galaxies are one of a kind, then we need to explain why they exist in the first place. But if astronomers find more of them, it could suggest that dark matter is not as universal as we once thought. This would shake the foundation of modern cosmology, forcing researchers to reconsider how galaxies form and evolve. One approach to solving this mystery involves using more advanced telescopes and observational techniques. Current observations of DF2 and DF4 have relied on measuring the movements of their stars to estimate their total mass. However, these measurements are incredibly difficult because they require precise calculations of distances and velocities across millions of light years. Even a small error in these calculations could lead to incorrect conclusions about whether a galaxy contains dark matter. To eliminate this uncertainty, astronomers are turning to instruments like the James Webb Space Telescope, JWST, and upcoming next-generation observatories that can provide even more detailed data. If future observations confirm that DF2 and DF4 truly lack dark matter, scientists will need to explore new theories to explain how they formed. One possibility is that these galaxies were created through a rare and unusual process that separated normal matter from dark matter early in their history. For example, some researchers have suggested that powerful interactions with other galaxies could have stripped DF2 and DF4 of their dark matter, leaving behind only their stars. But if this is the case, we need to understand what kind of interactions could cause such a dramatic separation. Could galaxy collisions or gravitational tidal forces be responsible? Or is there an even more exotic explanation that we haven't yet considered? Another possibility is that DF2 and DF4 formed in a completely different way than other galaxies. If dark matter is normally required for galaxies to come together, then how did these ones manage to form without it? One hypothesis is that these galaxies formed in a region of the universe where the conditions were different from those found elsewhere. Perhaps a unique combination of gas dynamics and gravitational interactions allowed these galaxies to grow without the need for dark matter. But if that's the case, why don't we see more galaxies like them? Is there something unique about their location or history that set them apart? Some researchers are even considering the idea that dark matter itself might not be real. Instead, they propose alternative theories of gravity, such as modified Newtonian dynamics, MOND, which suggests that the effects we attribute to dark matter are actually caused by a different set of gravitational laws. If MOND is correct, then DF2 and DF4 could be key pieces of evidence that support this theory. However, MOND itself has major challenges to overcome, as it struggles to explain many observations that the dark matter model accounts for. Still, the existence of dark matter-free galaxies adds fuel to the debate, pushing scientists to reconsider what they think they know about gravity and the cosmos. One of the biggest open questions is whether these galaxies truly contain zero dark matter or if they simply have much less than expected. While initial studies suggest that DF2 and DF4 have almost no dark matter, some researchers argue that small amounts could still be present but are just difficult to detect. If it turns out that these galaxies do contain a small fraction of dark matter, it could mean that dark matter behaves differently in certain environments, potentially revealing new properties of this mysterious substance. But if future observations confirm that these galaxies are completely devoid of dark matter, it could mean we are missing a crucial piece of the puzzle when it comes to galaxy formation. The implications of this discovery extend far beyond just these two galaxies. If dark matter-free galaxies exist, what does that say about the overall distribution of dark matter in the universe? Could it be that there are entire regions of space where dark matter is absent? And if so, why? These are the kinds of questions that astronomers are now grappling with, and the answers could reshape our understanding of the cosmos in profound ways. One of the most exciting possibilities is that dark matter-free galaxies could provide a new way to test our theories of cosmology. If we can find more examples of these galaxies and study their properties in detail, we might be able to learn something new about the fundamental nature of dark matter itself. For instance, if these galaxies formed in a specific type of environment, it could help us understand the conditions under which dark matter can or cannot exist. This, in turn, could provide valuable clues about what dark matter actually is and how it interacts with normal matter. At the same time, the existence of dark matter-free galaxies forces us to reconsider some of the most basic assumptions about the universe. For decades, scientists have operated under the assumption that dark matter is a fundamental component of galaxy formation. But if galaxies can exist without dark matter, then what does that mean for the larger structure of the universe? Could there be other forces or mechanisms at work that we have yet to discover? And if so, how do they fit into our current models of cosmology? As astronomers continue to study DF2, DF4, and other potential dark matter-free galaxies, They are also looking for alternative explanations that might resolve this mystery. One possibility is that our observations are simply incomplete. Perhaps there is dark matter present in these galaxies, but we just haven't been able to detect it yet. If that's the case, then more sensitive instruments and better observational techniques could eventually reveal the missing mass. But if further studies confirm that these galaxies truly lack dark matter, then we are faced with one of the biggest puzzles in modern astrophysics. Ultimately, the mystery of dark matter-free galaxies is a reminder of how much we still don't know about the universe. Every time we think we have a complete understanding of how things work, new discoveries challenge our assumptions and force us to ask new questions. Whether DF2 and DF4 are rare anomalies or the key to unlocking a new era of physics, one thing is certain: the search for answers is far from over, and the implications of this discovery could be nothing short of revolutionary. If these dark matter-free galaxies turn out to be more than just rare anomalies, we could be looking at an entirely new category of galactic structures that challenge everything we know. The reason this is so mind-blowing is that dark matter has been the backbone of our understanding of how galaxies form and behave. Without it, our entire model of cosmic evolution starts to look incomplete. Imagine if we discovered that certain galaxies could break all the established rules. What else could be possible? Could we have underestimated the true variety of galactic types out there? Could there be forces at play that we have yet to identify? These questions make the discovery of DF2 and DF4 one of the most intriguing mysteries in modern astrophysics. One of the biggest challenges in solving this puzzle is the sheer difficulty of studying dark matter itself. Unlike normal matter, which interacts with light and other forms of electromagnetic radiation, dark matter is completely invisible. We only know it exists because of its gravitational effects on visible matter. This means that detecting the absence of dark matter is just as tricky as detecting its presence. Scientists have had to use indirect methods, such as tracking the movements of stars and gas clouds within galaxies, to estimate how much dark matter should be there. The fact that DF2 and DF4 don't show the expected gravitational effects of dark matter has been shocking. But could there be errors in the way we measure these forces? Could the tools we use to estimate mass be leading us to the wrong conclusions? One alternative explanation is that these galaxies might have started out with dark matter, but something stripped it away. Some researchers have suggested that tidal interactions with nearby massive galaxies could have pulled away their dark matter halos, leaving only the visible stars behind. If this theory is correct, it would mean that dark matter can be more easily separated from normal matter under certain conditions, something we previously thought was nearly impossible. But there's a major problem with this idea. Dark matter is supposed to be weakly interacting. If it doesn't clump together like normal matter and only interacts through gravity, then how could a galaxy lose all of it? If dark matter can somehow be stripped away while the stars remain intact, it raises serious questions about how tightly dark matter is bound to galaxies in the first place. Another potential explanation involves exotic physics, things like self-interacting dark matter or even entirely new forces of nature. Some scientists have suggested that dark matter may not be completely passive and could, under specific conditions, interact with itself in a way that allows it to be pushed out of galaxies. This would mean dark matter is more complex than we ever imagined. If dark matter can be repelled or expelled from a galaxy, then we need to completely rethink our assumptions about how it behaves. This could also have massive implications for the broader universe. Could there be large regions of space where dark matter is sparse or even entirely absent? If so, how would that affect the formation of galaxies, galaxy clusters, and the large-scale structure of the cosmos? There's also the possibility that we've been misunderstanding gravity itself. Some physicists propose that what we call dark matter might not be a separate substance at all but rather a sign that our theories of gravity are incomplete. Modified Newtonian dynamics, MOND, and other alternative gravity models try to explain galactic motion without the need for dark matter. If DF2 and DF4 truly lack dark matter, then MOND could gain new support. However, MOND has struggled to explain many other observations in cosmology, so if it were the correct answer, it would still require major refinements. The discovery of dark matter-free galaxies might be an important clue in this ongoing debate, forcing scientists to rethink fundamental physics. One of the strangest possibilities is that dark matter itself is not as universally distributed as we thought. If some galaxies can exist without dark matter while others are completely dominated by it, it suggests that dark matter might be more dynamic and less predictable than we assumed. Could there be a cosmic process that selectively removes dark matter from certain regions of space? Or could dark matter itself behave differently in ways we haven't yet detected? These questions drive home the fact that dark matter is still one of the greatest unsolved mysteries in modern physics, and dark matter-free galaxies might just be the key to unlocking its secrets. At the heart of this mystery is the need for better observations. Current telescopes have given us a good starting point, but we need more detailed studies to confirm whether DF2 and DF4 truly lack dark matter. Instruments like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, will provide even sharper images and more precise measurements of these galaxies. If they confirm that these galaxies are genuinely devoid of dark matter, it would be a groundbreaking discovery that forces us to completely rethink our understanding of the universe. But if further observations reveal hidden dark matter that was previously undetectable, it could mean that our measurement techniques need refining rather than our theories. Either way, these galaxies are pushing the boundaries of our knowledge and forcing us to confront the biggest questions in cosmology. One of the most exciting aspects of this discovery is that it could lead to entirely new physics. Whenever scientists encounter an anomaly, something that doesn't fit within existing models, it often paves the way for revolutionary breakthroughs. Just as the discovery of strange atomic behaviors led to quantum mechanics, and the realization that light can bend around massive objects confirmed Einstein's general relativity, the mystery of dark matter-free galaxies could lead to a whole new understanding of the cosmos. Could we be on the verge of discovering a new fundamental force? Could dark matter be part of a hidden sector of physics that interacts with the universe in ways we have yet to uncover? The possibilities are endless, and the search for answers has never been more exciting. Ultimately, the discovery of dark matter-free galaxies is a reminder that the universe is far stranger and more complex than we ever imagined. Just when we think we have it all figured out, new observations come along that challenge our deepest assumptions. Whether these galaxies turn out to be anomalies or key pieces of a larger cosmic puzzle, they have already changed the way we think about dark matter and the fundamental forces that shape our universe. As scientists continue to investigate this enigma, one thing is certain: the answers we find will lead to even bigger questions, and the search for truth will push the boundaries of human knowledge further than ever before. If dark matter-free galaxies are real and not just observational errors or misinterpretations, they could force scientists to rethink everything about cosmic structure formation. For decades, dark matter has been the scaffolding upon which galaxies are built. If some galaxies exist without it, then it means either we don't understand how galaxies form, or we don't understand what dark matter actually is. Either way, something huge is missing from our understanding of the universe. Consider what this would mean for the standard model of cosmology. Right now, scientists believe that after the Big Bang, dark matter helped shape the universe by pulling normal matter into clumps where galaxies could form. Without dark matter, normal matter alone wouldn't have had enough gravitational pull to form the massive cosmic structures we see today. If galaxies can exist without dark matter, then does that mean there's another way for galaxies to form? Could normal matter alone somehow organize itself into stable galactic structures? This would go against decades of theoretical work and would require entirely new explanations for how the universe evolved. Another important question is how widespread these dark matter-free galaxies are. Are DF2 and DF4 just rare exceptions, or are there many more like them that we haven't found yet? If more of these galaxies exist, then it might indicate that dark matter is not as universally present as we thought. But if they turn out to be extremely rare, then they could simply be outliers, strange accidents of cosmic evolution that don't require us to overhaul our understanding of physics. The challenge is that finding these galaxies is incredibly difficult. Because dark matter is invisible, scientists usually infer its presence by looking at how galaxies rotate. If a galaxy rotates faster than expected, it suggests that there's extra unseen mass holding it together, mass that we attribute to dark matter. But in the case of DF2 and DF4, the stars themselves are moving much slower than expected, suggesting there's little to no dark matter at all. The fact that these galaxies seem to contain normal amounts of stars but almost no dark matter suggests that dark matter and normal matter don't always stay together. This is strange because, in most galaxies, dark matter and normal matter are thought to be closely linked. Dark matter is believed to form massive halos around galaxies, providing the gravitational pull needed to keep them intact. So how did these galaxies lose their dark matter? If dark matter can be stripped away, what does that mean for other galaxies? Could some of the galaxies we see today have once had more dark matter, only to lose it over time? If so, what could have caused this? One possibility is that these galaxies formed in regions of space that were already naturally low in dark matter. If that's the case, then maybe they didn't lose dark matter, they just never had much to begin with. But this would go against the idea that dark matter is evenly distributed throughout the universe. It would suggest that dark matter is clumpier than we thought, and that some regions of space might naturally lack it. This would be a radical shift in how we understand the structure of the cosmos. Another possibility is that dark matter was somehow pushed out of these galaxies by interactions with other galaxies. Some scientists have suggested that DF2 and DF4 might have passed close to a much larger galaxy that stripped them of their dark matter. But this raises another problem. If dark matter is weakly interacting and doesn't interact with itself in the same way normal matter does, then how could it be stripped away while the stars remained? If dark matter can be separated from normal matter this easily, then maybe it behaves differently than we thought. These galaxies also raise questions about whether dark matter is actually necessary to explain galactic rotation. If dark matter is real, then DF2 and DF4 should fall apart without it. But they don't. They remain stable despite having little to no dark matter. This suggests that either these galaxies formed in a completely different way, or our understanding of gravity is incomplete. This is where theories like modified Newtonian dynamics, MON, come in. MON suggests that instead of dark matter being an invisible substance, maybe gravity itself works differently on large cosmic scales. In this model, gravity might behave differently at very low accelerations, which would explain why galaxies rotate the way they do without needing extra unseen mass. However, MOND has problems too. While it can explain some galactic behaviors without needing dark matter, it struggles to explain larger cosmic structures, such as galaxy clusters and the cosmic web. It also doesn't fit well with our understanding of general relativity, which has been proven right time and time again. If DF2 and DF4 support MOND, then physicists would have to find a way to reconcile MOND with everything else we know about the universe. There's also the possibility that dark matter isn't a single type of particle but rather a more complex mixture of different particles with different properties. Maybe some types of dark matter interact more with normal matter than others. If that's the case, then perhaps DF2 and DF4 somehow ended up with a type of dark matter that is less gravitationally influential, or more easily stripped away. This would mean dark matter is far more complicated than we currently assume. Some researchers have even proposed that what we're seeing in DF2 and DF4 isn't a lack of dark matter, but rather evidence that dark matter itself is capable of behaving in unexpected ways. Could dark matter be dynamic, shifting in and out of galaxies under certain conditions? Could it be affected by forces that we haven't yet detected? If so, then this could be one of the biggest breakthroughs in physics in decades. One of the most exciting aspects of this mystery is that it's still unsolved. Right now, scientists are working on gathering more data to determine whether DF2 and DF4 are truly dark matter-free, or whether something else is going on. More observations with advanced telescopes will help refine our measurements of these galaxies, and may reveal additional details that could confirm or disprove the current theories. But no matter what the final answer is, these galaxies have already forced us to rethink what we know about dark matter and how galaxies form. The implications of this discovery stretch far beyond just a few galaxies. If dark matter can be missing from some galaxies, it could change how we search for dark matter in the first place. Most dark matter experiments assume that dark matter is everywhere and behaves the same way in every galaxy. But what if that's not true? What if dark matter behaves differently in different environments? If so, then some of the experiments designed to detect dark matter particles might need to be rethought. In the coming years, scientists will continue to study DF2, DF4, and other similar galaxies to see whether their findings hold up. If they do, then we may be on the verge of a scientific revolution, one that forces us to completely rewrite the rules of cosmology. If they don't, and we find hidden dark matter in these galaxies after all, then it could simply mean that our current techniques for measuring dark matter need improvement. Either way, these galaxies are a puzzle that has captivated astronomers around the world, and the search for answers is only just beginning. One thing is certain: the universe never ceases to surprise us. Just when we think we have everything figured out, something comes along that shatters our expectations. Whether dark matter-free galaxies turn out to be rare oddities or fundamental clues to a deeper cosmic truth, they remind us of one simple fact: there is still so much we don't know about the universe. And that's what makes space mysteries like this so exciting. Every answer leads to more questions, and the search for the unknown will continue to drive human curiosity for generations to come. The discovery of dark matter-free galaxies is not just a minor anomaly, it challenges the very foundations of modern astrophysics. If these galaxies truly exist without dark matter, it could force scientists to reconsider everything from galaxy formation theories to the nature of gravity itself. But before we rewrite the laws of physics, we need to explore every possible explanation, including those that might reveal something unexpected about dark matter's behavior. Could it be that dark matter isn't as uniform as we thought? Could it be affected by unknown cosmic forces that selectively remove it from certain galaxies? These are the kinds of questions that keep astrophysicists awake at night. To truly grasp the significance of this mystery, we need to understand the standard model of galaxy formation. According to current theories, dark matter acts as a gravitational framework upon which galaxies form. Without it, the pull of normal matter alone wouldn't be strong enough to form and hold galaxies together. This model has been supported by decades of observations showing that most galaxies rotate faster than they should if they were only made of normal matter. The only way to explain this discrepancy is to assume that a large amount of invisible mass, dark matter, is providing the extra gravity needed to keep them intact. But if dark matter is the glue that holds galaxies together, how do DF2 and DF4 exist without it? These galaxies don't behave the way they should if they lack dark matter. Their stars move too slowly, their structure remains stable, and they seem to contradict everything we thought we knew. This isn't just an isolated case of an unusual galaxy. This is a fundamental challenge to one of the biggest assumptions in cosmology. There are a few possible explanations for how these galaxies could have lost their dark matter. One theory is that they were once normal galaxies with dark matter, but some cosmic event stripped it away. A violent interaction with another galaxy could have pulled the dark matter out, leaving behind only the visible stars. However, this raises a major problem. If dark matter is weakly interacting and doesn't interact with itself in the same way that normal matter does, then how could it be stripped away without also pulling apart the stars? The idea that dark matter can be separated from a galaxy so easily suggests that it might not be as stable as we thought, or that it interacts with the universe in ways we don't yet understand. Another possibility is that these galaxies formed in a region of space where dark matter was naturally sparse. If that's the case, then maybe they didn't lose dark matter, they just never had much to begin with. But this would contradict the idea that dark matter is evenly distributed throughout the universe. If some regions naturally lack dark matter, then that means dark matter is far more complex and uneven than we currently assume. A more radical idea is that these galaxies are providing evidence that dark matter might not exist at all. If DF2 and DF4 can remain stable without dark matter, then maybe other galaxies don't actually need dark matter to hold themselves together either. This is the basis of alternative theories like modified Newtonian dynamics, MOND, which suggests that gravity behaves differently on very large scales. If MOND is correct, then maybe dark matter isn't a real substance at all, but rather a sign that our understanding of gravity is incomplete. The problem with MOND, however, is that it struggles to explain many other cosmic phenomena. Dark matter isn't just used to explain galactic rotation, It's also essential for explaining things like the motion of galaxy clusters, the distribution of cosmic microwave background radiation, and the large-scale structure of the universe. If Mond were correct, then we would need an entirely new theory of physics to explain all of these observations. On the other hand, if DF2 and DF4 do have dark matter, but it's behaving in an unexpected way, then this could be evidence that dark matter isn't just one type of particle, but a mixture of different particles with different properties. Perhaps some forms of dark matter interact more with normal matter than others, and DF2 and DF4 somehow ended up with a type of dark matter that is less gravitationally influential or more easily stripped away. This would mean that dark matter is far more complicated than we thought. Another possibility is that dark matter itself is dynamic, shifting in and out of galaxies under certain conditions. Could dark matter be affected by forces we haven't yet detected? Could it move through space in ways that cause it to accumulate in some galaxies while leaving others empty? If so, then this could be one of the biggest breakthroughs in physics in decades. One of the biggest challenges in solving this mystery is gathering more data. Right now, DF2 and DF4 are two of the only galaxies that seem to lack dark matter, but that doesn't mean they're the only ones. If astronomers can find more galaxies like them, then we may be able to determine whether this is a widespread phenomenon or just an isolated case. Advanced telescopes and better observational techniques will help refine our measurements and reveal additional details that could confirm or disprove current theories. If these findings hold up, then we may be on the verge of a scientific revolution. If dark matter can be missing from some galaxies, then it could change how we search for dark matter in the first place. Most dark matter experiments assume that it is evenly spread throughout the universe. But what if that's not true? What if dark matter behaves differently in different environments? If so, then some of the experiments designed to detect dark matter particles might need to be rethought entirely. Regardless of the final outcome, one thing is clear: these galaxies have already forced us to rethink some of our deepest assumptions about the universe. Whether they are rare exceptions or fundamental clues to a deeper cosmic truth, they remind us that science is always evolving. Every discovery leads to more questions, and the search for answers will continue to push the boundaries of human knowledge. And that's what makes space mysteries like this so exciting. Just when we think we have everything figured out, something comes along that shatters our expectations. The universe never ceases to surprise us, and the more we explore, the more we realize how much we still don't know. The search for dark matter-free galaxies is just beginning, and whatever we find, it's sure to change the way we understand the cosmos. The implications of dark matter-free galaxies go beyond just galaxy formation. If these galaxies exist and are truly devoid of dark matter, it raises serious questions about the way the universe is structured on both small and large scales. One of the most significant implications involves the distribution of dark matter throughout the universe. Current models suggest that dark matter is omnipresent, acting as a cosmic web that shapes the formation of galaxies and large-scale structures. However, the discovery of DF2 and DF4 suggests that dark matter may not be as evenly distributed as previously thought. If that's the case, then we have to reconsider the very fabric of the cosmos. Could it be that dark matter behaves more like a fluid, flowing in and out of galaxies under certain conditions? Or could it be that there are entire regions of space where dark matter is simply absent, leaving behind these peculiar galaxies? One of the most puzzling aspects of DF2 and DF4 is that they are relatively close to us in cosmic terms, about 65 million light-years away. If these galaxies were located on the edge of the observable universe, we might be able to explain their existence as some kind of anomaly that formed under extreme conditions in the early universe. But the fact that they exist in our cosmic neighborhood means that whatever process led to their formation could be more common than we think. Could there be thousands, or even millions, of galaxies out there that lack dark matter, but we just haven't looked closely enough to find them? The scientific community is still divided on whether DF2 and DF4 truly lack dark matter, or if there's an alternative explanation for their unusual behavior. One possibility is that we're simply misinterpreting the data. The methods used to determine the mass of a galaxy rely on indirect measurements, such as the speed at which stars orbit the galactic center. If there is some unknown factor affecting these measurements, then it could create the illusion that these galaxies lack dark matter when in reality they don't. Another potential explanation is that these galaxies are not actually as isolated as they appear. Perhaps they were once part of a larger galaxy that was torn apart by gravitational interactions with other galaxies, stripping them of their dark matter in the process. This would imply that dark matter can be separated from normal matter under the right conditions, something that would have profound consequences for our understanding of how galaxies evolve over time. One of the most intriguing aspects of these galaxies is that they contain large numbers of globular clusters, dense groups of stars that orbit a galaxy like miniature satellite galaxies. In most galaxies, globular clusters are relatively rare, but in DF2 and DF4, they are unusually abundant. Some scientists believe that this could be a clue to how these galaxies formed. Could it be that the presence of so many globular clusters is somehow linked to the absence of dark matter? If so, what does that tell us about the connection between dark matter and star formation? There's also the question of whether DF2 and DF4 are really unique. If these are the only two galaxies that lack dark matter, then they might simply be outliers, statistical anomalies that don't really challenge our understanding of the universe. But if astronomers find more galaxies like them, then we may be dealing with a major paradigm shift. Scientists are now searching for other galaxies with similar properties, and early indications suggest that there may be more out there. Another key issue is how these findings fit into the larger picture of cosmology. Dark matter isn't just used to explain the rotation of galaxies. It's also a crucial ingredient in our models of the early universe. If dark matter behaves differently than we thought, then we may need to revise our understanding of how the universe evolved from the Big Bang to its present state. Could it be that dark matter was more abundant in the past but is now disappearing from some regions of space? If so, what would that mean for the fate of the universe? Some researchers have proposed that dark matter might have different phases, similar to how normal matter can exist as a solid, liquid, or gas. If this is true, then perhaps DF2 and DF4 are located in a region of space where dark matter has transitioned into a different state, one that doesn't interact with normal matter in the usual way. This could explain why these galaxies appear to lack dark matter, even if it is still present in some form we don't yet understand. Others have suggested that dark matter could be influenced by unknown cosmic forces that cause it to accumulate in some galaxies while avoiding others. If this is the case, then dark matter may not be as passive as we thought. It may be an active component of the universe, capable of moving and shifting in response to forces we have yet to discover. One of the biggest challenges in solving this mystery is the difficulty of studying dark matter directly. Unlike normal matter, which can be observed using telescopes, dark matter does not emit, absorb, or reflect light. Its presence can only be inferred through its gravitational effects. This makes it extremely difficult to determine whether a galaxy truly lacks dark matter or if we're simply unable to detect it. However, new observational techniques and advanced telescopes may soon provide more answers. The James Webb Space Telescope, for example, has the potential to examine galaxies like DF2 and DF4 in unprecedented detail, allowing scientists to study their structure and motion with far greater accuracy than ever before. Future missions designed to map dark matter across the universe could also help determine whether these galaxies are truly anomalies or part of a larger, hidden pattern. Regardless of what the final explanation turns out to be, one thing is certain: these galaxies have already forced astronomers to rethink some of their most fundamental assumptions about the universe. If DF2 and DF4 are indeed free of dark matter, then we may be on the verge of one of the biggest breakthroughs in astrophysics in decades. If dark matter can be missing from some galaxies, then it could mean that we've been looking for it in the wrong places, using the wrong assumptions. This discovery could also have profound implications for the search for dark matter particles. For decades, scientists have been trying to detect dark matter using underground experiments, space-based detectors, and particle accelerators. But if dark matter behaves in ways we don't yet understand, then these experiments may need to be redesigned to take new possibilities into account. It's also worth considering the philosophical implications of this discovery. Throughout history, every time scientists have thought they understood the universe, a new discovery has come along to challenge their assumptions. The idea of dark matter itself was once a radical proposal, yet today it is accepted as a fundamental component of the cosmos. If dark matter-free galaxies turn out to be real, then it could mean that we are once again standing on the brink of a new scientific revolution. The search for answers is far from over, and the coming years will likely bring even more surprises. Whether these galaxies rewrite the laws of physics or simply add a new layer of complexity to our understanding of the cosmos, one thing is clear: the universe is still full of mysteries waiting to be uncovered. The idea that entire galaxies could form and exist without dark matter forces scientists to rethink one of the fundamental pillars of modern astrophysics. For decades, dark matter has been the invisible scaffolding holding the universe together, shaping the formation of galaxies and influencing their behavior. If galaxies like DF2 and DF4 truly lack dark matter, then it means there may be other, previously unknown mechanisms responsible for galaxy formation, mechanisms that don't rely on the presence of invisible mass. This not only complicates our understanding of how galaxies form, but it also raises the question of whether dark matter itself is as essential as we've always believed. Could it be that we've miscalculated the role of dark matter in shaping the universe? And if so, what does that mean for everything we thought we knew about cosmic evolution? One of the biggest challenges in confirming whether these galaxies are truly devoid of dark matter is the difficulty in measuring their total mass. Since dark matter doesn't emit or absorb light, scientists rely on indirect methods to detect it, mainly by observing how objects within a galaxy move. In most galaxies, the stars and gas clouds move at speeds that suggest the presence of a much larger, unseen mass. This is what originally led scientists to propose the existence of dark matter in the first place. However, in the case of DF2 and DF4, the movement of the stars suggests that their total mass is roughly equal to the mass of the visible matter alone, meaning there's little to no room for dark matter to exist. But is it really that simple? Could there be other factors influencing these measurements that we haven't considered yet? Some scientists have suggested that DF2 and DF4 may not be as unique as they seem, and that their apparent lack of dark matter could be due to an observational bias. It's possible that we're only detecting galaxies that fit a certain profile, and there could be many more galaxies with similarly low amounts of dark matter that we simply haven't found yet. If more galaxies like these are discovered, it would lend weight to the idea that dark matter isn't distributed as evenly across the universe as previously thought. But if these galaxies remain isolated cases, then we may be looking at an anomaly, one that demands an entirely new explanation. One possible explanation for how these galaxies could have formed without dark matter is that they were once part of a much larger galaxy that was disrupted by gravitational interactions with another galaxy. This could have stripped them of their dark matter while leaving their stars and gas largely intact. If this theory is correct, then DF2 and DF4 may not have formed independently, but rather as remnants of a once massive galaxy that was torn apart. This idea is supported by the fact that both galaxies are located near a larger elliptical galaxy known as NGC 1052, which could have played a role in their unusual formation history. But even if this were the case, it still doesn't fully explain why the dark matter would be stripped away while leaving the visible matter intact. Another intriguing possibility is that these galaxies formed in regions of space where dark matter is naturally scarce. If dark matter isn't as uniformly distributed as we think, then it's possible that some areas of the universe contain very little of it. This would imply that galaxies can form in a variety of ways, some with dark matter and some without. If true, it could force astronomers to completely rethink how galaxies come into existence and evolve over time. It would mean that dark matter isn't a necessary ingredient for galaxy formation, but rather one of many possible factors that influence how galaxies take shape. Then there's the possibility that DF2 and DF4 aren't actually missing dark matter at all, but rather that the dark matter in these galaxies behaves differently than what we're used to. Some theories suggest that dark matter could come in different forms, with different properties depending on its environment. If this is the case, then perhaps the dark matter in these galaxies exists in a state that doesn't interact in the same way we expect. This could mean that dark matter isn't entirely absent, it's just hidden in a form we haven't yet learned how to detect. Another mind-bending possibility is that the existence of dark matter-free galaxies could point to flaws in our current understanding of gravity itself. Some alternative theories to dark matter, such as modified Newtonian dynamics, MOND, suggest that the observed effects attributed to dark matter could actually be due to differences in how gravity behaves at very large scales. If this were the case, then the discovery of galaxies without dark matter might actually be evidence in favor of these alternative theories. Could it be that we don't need dark matter at all, and that our entire understanding of gravity needs to be rewritten? One of the biggest mysteries surrounding DF2 and DF4 is their unusual number of globular clusters. In a typical galaxy, globular clusters are relatively rare, but in these galaxies, they are abundant. This has led some scientists to speculate that the presence of so many globular clusters could be linked to the apparent absence of dark matter. Could it be that the formation of globular clusters somehow influences the distribution of dark matter within a galaxy? Or could the process of forming these clusters actually drive dark matter away? The more astronomers study these galaxies, the more questions arise. If these galaxies truly lack dark matter, then how do they remain stable? In most galaxies, dark matter provides the gravitational glue that holds everything together. Without it, galaxies should be more susceptible to disruption and destruction by external forces. Yet DF2 and DF4 appear to be relatively intact. Could this mean that other forces, perhaps related to interactions between stars and gas, are playing a more significant role in galaxy stability than we previously thought? New telescopes and observational techniques may soon provide more answers. The James Webb Space Telescope has already begun observing distant galaxies with unprecedented detail, and future missions dedicated to studying dark matter could help shed light on the mystery of these galaxies. One such mission is the Vera C. Rubin Observatory, which is set to conduct a massive sky survey that will help astronomers map out the distribution of dark matter across the cosmos. If more dark matter-free galaxies are discovered, it could change everything we thought we knew about the universe. Even if DF2 and DF4 turn out to be rare exceptions rather than the rule, their existence still presents a major challenge to our understanding of galaxy formation. Every time astronomers discover something that doesn't fit into existing models, it forces us to rethink our assumptions about how the universe works. Whether these galaxies rewrite the laws of physics or simply introduce a new puzzle to solve, they are a reminder that the cosmos is still full of surprises. If there's one thing history has taught us, it's that science is never truly settled. Every great discovery raises new questions, and every new question brings us closer to a deeper understanding of the universe. Dark matter-free galaxies may be an anomaly, or they may be the key to unlocking one of the greatest mysteries of modern physics. Either way, the search for answers is far from over, and the next big breakthrough could be just around the corner. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.